Alright, hell yeah. So we have my second customer. This is a college student that I saw doing math at the coffee shop and is also getting a minor in engineering. So we're going to do statics. And the two books that I have, this is what I went to school for. This is Pytel Kusalis, and this is Statics by Hibbler. So booyah. So that's kind of what we're doing today. And we have this going on. And it's just kind of interesting because he was kind of going over where he was stumped for some of his problems. And it's just kind of fascinating. I struggle to keep up, just with other people's modes of solving problems. You know what I mean? Where I have to start from the basics of what I know, build upon that. But I think it's cool. What we're going to try to tackle with this one is what's some take-home points that we can see from this. And so I think let's start there, just so we have something good within 5 minutes. We have a roller support over here, so that's just going to be one known force. And I did do a printout of things like your supports and then your reactions. So, if I do have friction and a chair, like on a sloped surface that does have friction, we're going to have a normal force in the direction of that contact, and then we're going to have a friction force. Cool. If you don't have friction, you just have a normal force in the direction that's perpendicular to the slope. So we're getting closer to what we have. If you have a roller, also just perpendicular. It can either be like a bearing, a ball bearing, or a series of bearings that are able to roll, and you basically just have a normal component. Cool. And then a pin connection. A pin, you can pull on all directions. So, hell yeah. Alright, hell yeah. And so here's my demonstration of a pin connection. Think of a pin connection, if you think of it as really loose. So if this is my pin and I just have a lot of room in here, this pin is floating until, I can take this pin and then force it in a direction. And if I do so, booyah, it's going to make a contact that's in the direction that it would be moving. So if I put a force on this pin in this direction, the contact point is going to be in that direction. Now if I put a force in that direction and this washer resists that force, I'm putting a slight force on it because we got some friction. This washer is having to push back against that. So let's see where it shows this pin. And a pin connection, what we say is that it's just going to be two components. So it can have a component in the horizontal and the vertical. So if I put a force in the horizontal and this washer resists this force, then it's going to be pushing that way. If I put a force in the vertical and this washer has to resist this force, the force is going to be that direction. Now I have to slow down and be very careful of what this says. This says that this bar is this member with a hole in it, and the pin connection is going to provide the force. So same deal. The pin is going to be a force. Let's say it's at a 45 that way. It's going to have a component this way and that way. And so on this diagram, you would have a resultant force. Let's just say it's here is your resultant. And what's causing that force at this pin is this loose pin is being pushed at that direction. So there you go. So that's the same deal, is that now this force has two components, one up, one over, and so wherever the resultant is going to be the contact of that pin on that member. Alright, hell yeah. And so this is going to be my favorite part, just because, what gives? If you do have members like these that are have two holes at the end and that can have pins, what's the deal? And what's going to happen? And so let's read about this first, because this is a two-force member, so I kind of burned this off. And let's just read all the way through, because this is something that, hey, would just kind of take 2 seconds to go over. So let's try it. 2-force member. And they even have like a noodle-shaped rigid body. Let's say it's made out of steel. It's just in the shape of a curve. And it says, as the name implies, 2-force member only has 2 forces applied, and they're applied at 2 points on the member. And so what that means is there's no moment. And so, we have 2 forces, but at this point I don't also have a moment. So keep that in mind, because actually it would be better if you think of this 2-force, you just say it, 2-force, no moment member. Just kind of for something fun in your head, just be like, oh yeah, there's something extra going on here, and it's the fact that we don't have something going on. We don't have a moment. So 2-force, no moment member, that's what we have. And so I'm going to definitely explain that in a second. In the foreshadow, sometimes it's just, just get there. If I put an upward force on this, if it's to be in equilibrium, I have to have a downward force over here. But if I apply an upward and downward force, we get spinning. So the only way I can apply an upward force on this mass and a downward force on this mass and prevent it from spinning is if I had a moment to, but I don't have. I have no place to put that moment. So this is going to say that the only way that I can put a force on this point and this point, to where if I put any force on these, and it has to be axial. So I can put a force in this direction, and I can put a force in compression. So I can put a tension force and a compressive force. If I try to put an upward force and a downward force and try to maintain equilibrium, I can't do it. It's going to spin. And I think that's counterintuitive, because you have a problem. You're just like, well, why can't you? Why can't on this, like any of these, why can't on this member can I have a net force in that direction and a net force in that direction and keep it from spinning? You just can't. The internal forces we'll see are just in compression or tension. And I don't know. So now I think that deserves a full read-through. Alright, hell yeah. So, as the name implies, a 2-force member has forces applied at only 2 points on the member. An example of a 2-force member is shown in figure 20A. And I always say, if you're reading textbooks, anytime it says go to the figure, literally go to the figure, go to the actual A, B, or C, look at the darn picture, and see what they just said. We have 2 forces. Cool. To satisfy this force equilibrium, this force Fa and force Fb must be equal in magnitude. Fa has to equal Fb. And opposite in direction, where the sum of the forces has to be 0, and this is a vector, so in all directions. So if I had, and they'll probably get to it in a second. So figure 520b, shows that Fa and Fb are the same. Must be equal, and they're going to be equal to F. So now we just say, hey, these two Fa and Fb are equal to F. Hell yeah. Furthermore, moment equilibrium, so that's the sum of the moments, requires that Fa and Fb share the same line of action. And that's what I just showed. If I take the moments about Fa and I have a component of this force perpendicular, any component, well, I would have to resist that with a moment at A, or some third force on this member, but it's only a 2-force member. So I either have to have a moment at A or B, or, and I don't have that. By definition, we just have 2 forces to deal with. Cool. They have to share the same line of action, which can only happen if they are directed along the lines joining point A and B. So therefore, the sum of the moments at point A have to be 0, and the sum of the moments at point B have to be 0, the net moment. That's true for all statics problems. You take the moment anywhere. The moment about this point has to be 0, and we can see that this distance, is some distance. We have a force that direction, causing a positive moment. So in the direction of the distance, sweep our fingers in the direction of the force. Now this one, same distance, and then sweeping our fingers in the direction of this force. those moments balance each other. So never forget that with statics problems, you can sum the moment about any point. Hell yeah. And that's going to be this figure F, figure 520C. Therefore, any two force members to be in equilibrium. The sum of the moments have to be 0 for a two force member to be in equilibrium. The line of action has to, that's a big sentence. The forces have to share the same line of action. Share the same line of action. Sweet. You know what I mean? It's good if I wouldn't say that out in public. It's good to in the textbooks reiterate what the textbook is saying, because it's usually gold. It's just hard to wrap your mind around. All right, hell yeah. Therefore, for any two force member to be in equilibrium, the two forces acting on the members must have the same magnitude. So this is kind of just recapping. Act in opposite directions and have the same line of action directed along the line of the joining 2 points where these forces act. And cool. And what did we just... And I think this is good to kind of take this home, because we just said that a pin connection has... well, I think it's devious here, because it looks like a pin connection has two forces on the pin, an X component and a Y component. But as a vector, this has magnitude and some sort of direction. And so a pin, and let's show it again, can only put a force, a pin, whatever it's touching, the contact point is the direction of that force. So if you can identify a pin, keep in mind that it has two components, but just know that it's just one force, one resultant force in a particular direction. That's where, this really comes home with the two force member being, if I have a force over here, or if I have two pin connections, knowing that this, all I can do, I can put a force in a contact direction, and it's going to have, and it is good to go back to this, it's going to have a horizontal and vertical component. So if I keep this member horizontal, and I put we'll just keep it simple and put a force this direction. To keep it static, I got to put an equal and opposite force the other direction. So I think you can see that. And again, what this two force member is saying is that if I put an upward force here on this member, you know what I mean? It seems like, well, I could balance it with a downward force, but that's just going to make it spin. And so, hell yeah. And now I'm going to go over the free body diagrams of this, because even just having this on the sheet of paper, you're just like, well, there's a lot of friction, and then so what gives when it comes to kind of just looking at this from a free body diagram perspective. Because I like to do the pretend it's in outer space. And this problem's cool because it's a problem where they say neglect the weight of these members. We're just going to say they're very lightweight, maybe like plastic, you know what I mean? So we have a very lightweight 3D printed plastic structure. It could be even just this size. And it could be strong enough, hell yeah, you just imagine it, that you could actually put, I mean, this size, you could maybe put your body weight into it. If it's this size made out of plastic. And maybe it's a little bit bigger, but right, you could break the whole system with your body weight, and potentially you might be at most be able to put your body weight into this, lean into this, and keep this structure from breaking. So that's kind of cool. So now we have some sort of idea of kind of looking at this thing. All right, hell yeah. One more thing that's going to come up with this problem, and this is always good to do with the wrenches, is let's say I'm just firmly holding this, and let's say it is just totally rigid, and I take this as my pin, because we're going to look at this. I'm going to apply a force on this pin, and I'm going to push on it in this direction. And so does anything happen to this member? Not really, you know what I mean? It is still just chilling, like nothing's happening to it. Same thing, if I hold this totally rigid and then pull this direction, you know what I mean? Nothing technically is really happening to this member. I don't know why I just did that. I just think that's good going forward, because what I'm going to be talking about is these pins. Because we're we're going to do my style of breaking this thing up, and we're going to do free body diagrams. And I guess you could do quite a few, because one, you could take this whole rigid structure and just pretend that it's not even, just pretend that it's like a trapezoidal piece of plastic. If this whole thing is a trapezoidal piece of flat plastic, and then you put a force on it, you're going to have a resisting force here, and you're going to have two forces there. So that can be one free body diagram. Cool. And then you can just remove one of these members, and take the remaining members, and then that's also a free body diagram. And so you can start eliminating members, and then do a resulting free body diagram out of the last piece. So we'll see how technical we get, because we don't want to make this a 3-hour video. Alright, hell yeah. I mentioned that because we can also just, take one member. We can get down to one member, and then we can have forces on it, and we can see how it's in equilibrium. Alright, hell yeah. And okay, I'm gonna jump ahead. So I'm gonna say that this member AB is just this, and then this member AC is just this. And then hell yeah. And then so let's say we pull a force in this direction, and we're just going to say the direction is horizontal. You know what I mean? So just one step at a time. And so if I do pull a horizontal direction, alright, hell yeah. Alright, hell yeah. This is going to work. Okay, so if I pull a horizontal direction, this kind of explains what I was doing before. It's just like, hey, just this member is in tension. Like, why isn't this doing anything? You know what I mean? If I just pull in this horizontal direction, and it's, see how, like, this is just like links in a chain? So that's kind of the first thing that maybe you can see, is that if I'm pulling, on all these links in a chain, these are just chilling and they're just hanging out. Alright, and this will be a good demo for me, because even though this is a statics problem, and if I have this one at this angle, if I choose to just put a horizontal force, you know what I mean, what's going to happen is that this thing is just going to rotate down. So ways that I like to think about this is, let's say I have a string right here going over the table, and I just have a weight over the table. And then the string is just frictionless with the table, and the string is able to move in this direction. And so that's how I visualize a force. If I'm trying to keep a force just in that direction, this thing is going to go like this and then maintain equilibrium. So that is going to happen. And I think that's useful, even though this is a statics problem and you're just like, okay, it looks like everything's rigid. I don't know. Maybe it's not. Maybe when you go to do this, you're just like, no, it's like easily, this isn't even, it's a dynamics problem right off the bat. But once you get here, then you're going to have equilibrium. And so, cool. Alright, hell yeah. And this is slow going for me, but this is good, because we just said member AB can really only, just be pulled this way or that way. We're trying to prove that two-force member deal just by kind of observation. And this one at an angle, really, the only thing we can do on it is pull it in tension this way and compress it this way. You know what I mean? If this member is just chilling by itself at this angle, we just went over that, and I put a force in this direction, it really wants to do this. You know what I mean? And then just maintain equilibrium and become a two-force member. You know what I mean? So if this is the direction of the force, hell yeah, this would be the two-force member. Now, if it is at this angle, you know what I mean? Hell yeah, we can, this is the direction of the two-force member. The forces are either being applied in tension or in compression. Alright, hell yeah. And I'm slow rolling this because we do have a downward component of this force. And that's what I like to do. I like to solid in the actual arrow for the vector for the force, and then do its components with open arrows. So it's just kind of my, I don't know, and I think some textbooks do that. So this is P, this is going to be Py, so this is vector P. This is PY and this is PX. Cool. Alright, so this is wild, because this is the crazy thing. This is where you get tripped up, is you're just like, this whole thing seems like a rigid system. Or, I mean, it's like a rigid system, whatever. But it's just kind of bizarre to think of these individual links as, well, even as like chunks of a chain. They're different than a chain, because a chain can only take tension. If this was, you know what I mean? But it's not too much different than a chain, because a chain can only take tension. The only difference between these members is they can only take tension and compression. They can't take anything else. You know what I mean? So they are very similar. I mean, they're analogous to the chain, but just halfway. So again, I'm going to relay point AB. This member AB can only take a tension or compression in this direction. If I have a force downward, this PY cannot... AB can't do anything. It's just throwing up its arms. You know what I mean? It's just like, I can't do anything for you. If you're putting a force down, hey, AB is just going to go with the flow until it actually balances out with that downward force. And if the resultant force, if you just had AB just chilling out with nothing else, and it was just on this pivot, that would be pretty easy to see, where you would just have the force in this direction. It would be balanced once this member is in that direction. So we can show that with a demo. If I'm going to put this downward force with P, then it's just going to be balanced until this member is parallel to that direction. Hell yeah. Alright, hell yeah. So now I'm going to start talking about these pins in general. We can even make a bigger pin. It's not going to fit, so let's just use these. So here's our pin at A. It's a chunk of metal, and we're going to apply a force on that pin with this vector P. So we're going to apply a downward force of PY and a force to the left of PX. Alright, hell yeah. I'm trying to make a simpler problem, and I think I just did it. So we're going to say this is member AB, and then this is member AC, and we're going to make it vertical. So AB is horizontal, member AC is vertical, and then we're going to have this vector. P is going to be at this angle. It's going to have a PX component and a PY component. What's going to happen is that this vertical component PY is going to be taken by this member. Like, that's what it wants to do. It's a two-force member. We've kind of... I think I've thoroughly proved that for myself. That's my only objective, is just to, if I understand it and I walked my way through it, maybe you can, you're kind of following along. Hell yeah. And then this PX force can only be taken by AB. And you know what I mean? And I could just juggle this 1,000 different ways. You're just like, hey, the PX force can't be taken by AC. You know what I mean? But it can be taken by this AB. Hell yeah. You know what I mean? This PX force in this direction can be taken by AB. So that's the simpler problem. So what happens when this one's at an angle? And there's a lot of different ways to look at this when you have something at an angle. I always like to think of like a shopping cart. Where you're, you know what I mean? You're just pushing at a downward angle because... you know what I mean, we're taller than the shopping carts. And so, whoops. But yeah. So you're pushing at a downward angle. Like, only the component, I'm going to do these little arrows. Only the component in this direction is giving you a force that's overcoming friction. And heck yeah, you got some motion, change in velocity. Now you're not accelerating permanently. Your change in velocity isn't just exponential, because hell yeah, you still got a lot of friction. They don't replace these too often. I always do like 3 and then toss them to the side and then grab my favorite one. Every time I go grocery shopping. Hell yeah. All right, so sweet. So like what? Let's say we need something that kind of makes sense. We're pulling this direction. Let's say you have like a big cement block, on the ground. Just something hella heavy. It actually and you have a rope, same thing. It's kind of like the shopping cart analogy. and you need to put a force in this direction. That's what you're pulling with, and you have to overcome friction. You know what I mean? You have the weight of this mg, you have a normal force, and then obviously you have a frictional force, force of friction, mu n. You know, and you have to overcome. This is a statics problem all day, where the sum of the forces, so this has two components. This is Fx, this is Fy. This is going to be statics all day if the sum of the forces in the x direction are 0. And, you know what I mean, you have and let's just say this is the positive x direction. And so you have a negative Fx plus mu n is equal to 0. And so, cool. I'm probably forgetting something here, but obviously this mu n is just a max. Like this is, you know what I mean? Because like this isn't applying it. Just because something's resting on the ground doesn't mean it's like wanting to go the other direction and has a force the other direction. It's just the fact that this will always balance the Fx. So up to the value of this. So this has some sort of value, and so we can rearrange this equation. Fx is equal to mu n. And as long as this is less, and this value is known, you know, when we do tests on friction. And so if Fx is less than or equal to mu n, we're going to be a statics problem. All right, why am I doing this? I'm doing this just to show that this force has to be bigger than this component. You know what I mean? So if there's a point where this block moves, it's where my force is equal to, you know what I mean, the force of friction times the weight of this thing. And it only moves when this horizontal component is equal to that. But if I'm pulling up like at a let's just say 60-degree angle, you know, with a 60-degree angle, what happens is this horizontal component's only 50.5. You know, that's cosine of 60. And so it's just going to be 0.5. It's going to be 50%. So if I'm pulling up with like 100 pounds, only 50 pounds are in that direction. And so I'm bringing this up because what we need to do is be able to do this problem where we're just like, hey, I need to do something in reverse. Like what I'm doing is like, hey, I need to support, I'm putting a downward force on this pin of Py. I need to support it, but in a not a very efficient way. Like literally, if I had to support this pin by applying tension this direction, if I had to support it by applying, you know, if I had to push, if all I can do is push linearly with this, and I have a downward force, this would be the best. And then over here, you know, I can push it this way, but if I have to resist this downward force, it's only a component of that. Like, oh, and I'm not liking this geometry of how these things. So let me think about this. Alright, hell yeah. So here's one way to think of the problem is a little easier, because I just got into the issue of being like, well, if I push up on this, like it's going to move that way, and it doesn't feel like I'm pushing directly up, but hell yeah. So let's say if I have this, you know, this pin up here, and someone's like, hey, can you push up? And this pin's just really heavy. Let's say it weighs 20 pounds, and you're a person standing underneath it, and you have a table in the way, and you're standing right here, and you have to push with your arms in this direction. And someone's like, hey, can you keep that, you know what I mean? Hey, hold this and hold this up for me. And so when you go to hold it up, the only way that you can actually push on it is in this direction. And so, but it still weighs 20 pounds, and so you're going to have to actually push quite a bit. And let's say it is resting up against a wall. So that's just mentally what I was thinking. Just try to make a simpler problem. And so I have this chunk of metal. It weighs 20 pounds. It's rounded, maybe like a bowling ball type thing. I can get my hands around it, and but I can only push in this direction. You know, I can't cup underneath it and push it directly up. I can just push it, and I know I'm pushing it against the wall. You know what I mean? Like, that's not technically helping, but it's just I can push against the wall. And so in this, because of this angle, because it would be better if I was just directly underneath it and pushing it straight up and holding it in place. Because I'm pushing at such a bad angle, I'll have to push harder. So that's it. You know what I mean? That's all. And this problem, just in general, it's good to get your trigonometry just based on intuition. And so what I do for that is we have a 3 and a 4. You know what I mean? So before we do the whole 3, 4, 5, you know what I mean? Because we have a 3, 4, 5 triangle here, is just look at this from a geometry perspective. So I always like to take, this is the hypotenuse and this is a right triangle. I always like to take the hypotenuse and divide it into 2, and then just visually compare it to maybe the shorter side. You know what I mean? So, because I know this is, because let's say this is a vector where I'm pushing, I'm just going to say I need to push 100 pounds on something because it's real heavy. I just do 100 because I can break it up as a percentage. So if I'm pushing 100 pounds and we just made this not a bowling ball but something even heavier, and let's see, if I can push 100 pounds, what's the heaviest? That's another question. What's the weight of this metal, or you know, just a big old heavy ball, medicine ball or something? What can be the weight of that medicine ball if I can push with 100 pounds at this angle? Because I could do that. I just look at the components and size these vectors up. So this one is 100. That would probably come to about here. So this is about 60. You know what I mean? Cool. And then how about this one? Typically, and this is what I always say, if this angle is 30 degrees or less, you know what I mean? If you have triangles, this is like a 30-degree triangle, and if I'm going to say this is 100, you can always just approximate this to be 100. That's using the small angle theorem up to 30 degrees. And I mean, we're just saying that this line right there is about equal to that line. And it's not, it's 86.6. You know what I mean? You get 0.866 is the cosine of 30. But up to 30 degrees, you can always approximate this. You know what I mean? Because it doesn't, you know what I mean? And if you went less, if you did like a 20-degree triangle, well, I don't know. If that's the right triangle, this length is pretty much equal to that length. It might be 90% of it. So it's just good to kind of, yeah, have just ability to guess the components of right triangles. Alright, so from that visual perspective, I don't know, I just chop it up even more. We got 75%. Hey, this looks a little bit bigger, but it's probably pretty close to 75%, a little bit bigger. And then you can do the 3, 4, 5. What's the 3, 4, 5? Well, you're going to say this length is equivalent to, well, you do this. Like you have a slope where this would be 3, this would be 4, and this would be 5. And that's exactly what we have. I mean, this whole triangle here, this height is 4, this height is 3, so this height is 5 feet. And when we do have this triangle going on, what we want to know is this side as a percentage of this hypotenuse. That's what I always think. I always think of sines and cosines as being percentages of the larger number, which is the hypotenuse. When we, especially with a problem like this, all our vectors are going to be along these members, and these members are going to be the hypotenuse of right triangles. Cool. And so, yeah. So what are the percentages of these? So this would be the percentage of this compared to that is 3 divided by 5. You know what I mean? And so to do this mental math fast, always get your, if you can, get your denominator as a factor of 10. So I'm going to multiply top and bottom by 2. Now that my denominator is 10 and this is 6, and then you're just like, oh hell yeah, just move the decimal place 1 and we got 0.6. And if I multiplied it by 100%, that's going to be 60%. So 3/5 is 60%. This length is 60% of the hypotenuse. How about 4/5? Same thing. Get your denominator to be a factor of 10. We got 8 over 10. That's 0.8. Multiplied by 100%, that's going to be 80%. So the 3, 4, 5 triangle, this is going to be 80% of the hypotenuse. This is going to be 30% of the hypotenuse. So now let's go back to this as a vector. If this is 100 pounds, I can have an upward component of 80 pounds, and into the wall, I'm going to be pushing 60 pounds into that wall. So I can hold, if point A is a pin that weighs like a medicine ball, or just a chunk of metal that weighs 80 pounds, I can push it at this angle and hold it. I can push 100 pounds at this angle and hold it stationary. I can, with something that weighs 80 pounds. Booyah. All right, hell yeah. So I took a little break, and I just thought, yeah, this is so cool. Because with a heavy medicine ball that weighs 80 pounds, we need to support that vertically. And we said it's pushing up against the wall 60 pounds. And that was a simplified example. But guess what we don't have? We do not have a wall, and we're still pushing this 60 pounds that way. That's why this was hard for me to represent by pushing this way. You're just like, well, it doesn't feel like you're understanding how much is being pushed upward by pushing at an angle like that. But if we do have a wall, hell yeah, you can see that we're pushing 80 pounds up, 60 pounds into the wall, but we don't have the wall. So that's where a B comes in, is that I'm pushing 60 pounds this direction, but I don't have the wall, and I still want this medicine ball to be stationary right there, and so AB has to pull this way 60 pounds, So, to make sure that medicine ball is going to be at that location. So now if someone says, hey, with a team of 2, one person has to push 100 pounds and reach over this table, this medicine ball, but they can only push that direction. And this person, AB, I guess has a string attached to the medicine ball and can only pull this direction. Well, hell yeah, you'd be able to support that. And so, so cool. So that's fairly good representation of what's going on at point A. And it's kind of interesting that we treated this pin as the heavy thing in it. And I don't think people would generally look at a problem like this and think the pin is the heavy component. A pin is maybe the lightest weight chunk out of this whole structure if this was a bridge or something. But if you think of the pin as being just a heavy chunk of mass that has to, well, I don't know. In that regard, we were just treating the pin as a heavy chunk that had a downward force of, just weighed 80 pounds. And so I guess the next leap is to assume that, well, you are, if we're saying that a medicine ball weighs 80 pounds, and that's going to be this point A, or like the pin, that just gets its force because you have an earth underneath this. And so I think if you're not, every problem, literally, if you're not writing the force of gravity equation as the gravitational constant times the mass of this pin A times the mass of the Earth divided by the radius of the Earth squared, I just feel like you're missing out. Because, sure, if point A was a medicine ball that had, its weight would just be mg. So you see this all day in statics, and only the first chapter is going to say, what is that mg? Well, it comes from the m is this part right there, and then the g is these three things. You know what I mean? And the gravitational constant is a constant. Mass of the Earth ain't changing. And literally, it's kind of interesting. The radius, and this is two spherical objects. You know what I mean? So if you have, this is the mass of the Earth, and this is the mass, you want to take the center of mass of the Earth and the center of mass of whatever your, and then you're going to take the distance between those. Well, we just have a huge Earth, and then this chunk of mass is just right at the surface. You're still going from center point to center point, but the Earth's surface is just so big that that distance to the center just overwhelms, this distance to the center of this radius, where like this little extra bit is just completely negligible. And it doesn't even matter if you're at sea level or at the top of Everest doing that. Even the distance from the center of the Earth to the surface of the Earth to the top of Everest, whether you have this experiment, this medicine ball at the beach or the top of Everest, the distance between those is very negligible, where this number hardly changes. It's that 9. It's 10. It's 9.8, 9.81, or just 10 in general. And so that's kind of where that number comes from. And I don't know. I just think forces are what we're used to. Like, we have a good understanding of forces, especially when we get into material mechanics. The forces are associated with pressures. Like, the changes in length are a lot harder to ponder. But so, because forces are so related to weight, like lifting weights, the force of things, I think any problem that has applied forces, where you apply the forces, I think can be, like, I always do like this in my mind. If I had to like model these, and if I had to do this on a table, and I had to, and so we have this situation going on like this, and then we got a couple pins there. If I had to model a force in that direction, what I would do is just tie a string on here, and then support like a weight, something heavy, can of soup or something. You know what I mean? And then just kind of have this as like a perpendicular roller here. And you could even put that roller like on bearings. You know what I mean? So this string is on bearings, and then that is being applied, and that's going to be a force applied. I don't know. I don't know why I just had to do that, but I think even just applying a force at a point, that's the equivalent of doing this, and so still it's just like, I guess it's like that like if you're pulling on something this way, that doesn't require any gravity. So that's kind of fascinating that a lot of force is leveraging of materials. It's yeah, I don't know why I'm at a loss for even, it's just like, a screw and a bolt, or like a bolt and a bolt and a nut. You know what I mean? Compressing a washer. You're just jamming stuff in between material, and you already have physical attraction between materials, and so you're just using other materials to like wedge other materials apart, generating those forces. So it's kind of interesting where forces come from and how you can apply forces. But for whatever reason, I just think they're pretty intuitive. Potentially it's because we just have such a understanding of gravity. You know what I mean? If something's hanging out over a cliff and you're hanging on for, you can't hang on for very long. You know what I mean? Because gravity. Alright, hell yeah. So now I want to spend a couple minutes trying to reassess my understanding is that this force is applied at the pin. And I want to assess like why it's not applied at the member, and would that make any difference? You know what I mean? If I just apply this force on this chunk of metal, like tie a rope to it and then pull this member that way, isn't that the same? Alright, hell yeah. And so kind of the first chapter is, if we're just looking at external effects, like if I have this as my member AC, it's going to be equivalent if I come in here with a pin and push on that surface at this angle, as the same thing as attaching a rope and then pulling on this outer surface. The line of action of those are going to be the same. And when we're just talking about external effects, those are going to be equivalent. Alright, hell yeah. So I've gotten into the habit of kind of reading textbooks and just kind of knowing where things are. And some things are in the first chapters, so let's see if this will focus in. So this is having those three, so we have like 3 bars, let's say. And you can either put the forces on either side of the bar, and I apologize, I haven't gone over kind of the Newtonian perspective of like if this is a mass and we're applying a force on it in one direction. Like if you just had a force in one direction, it would be traveling across the universe in that way, accelerating. But if we have an equal and opposite forces, hell yeah, we got the definition of just chilling, definition of statics, and that's kind of what we're into. But if this chunk of mass also is a rigid body, where and the definition of a rigid body from this definition is if I put a force here and a force there. This thing does not change in length. Even though we'd know from material mechanics that, once we get into that aspect, things do lengthen, but negligible anyway. So we still consider them rigid bodies from that perspective. I think I have that right. And then we have 2 forces compressing in. And so, and then we have this, where we have a force pushing in on A, and then just next to it, maybe we have a force, pushing the other direction. And so in both of these, if we're just analyzing the rigid body itself, this rectangle is a chunk of mass, and we want to know if it's not moving across the universe in these perpendicular directions or spinning, we still want to make sure it's not a dynamics problem. We can see that this force is balanced by that. And so that kind of shows that rigid body. What does this even say? Let's read it. If the bar is rigid, meaning that the deformation is negligible, there will be no observable difference in the behavior of the 3 bars. In other words, the external effect of the 3 loadings are identical, and it follows. Oh yeah, what we were talking about is that as these vectors. Oh, and they already do it. They take this. And then they say, well, can't we just move this point to point A? And yes, we can. And so it's a sliding vector. And so that's the principle of transmissibility. And then we have a sliding vector. So this vector can move to there, and this vector can move back to this point. Cool. All right, hell yeah. But now I'll get into it because from like going back and doing some of these college-based subjects is like the one thing, like what's the take-home point? Because I even forgot I didn't even know what a rigid body was. That's such first chapter stuff that you're just ready for the equations, and I don't pay attention to those first chapter stuffs. But from the Newtonian perspective, is that if we do have a chunk of mass, and I apply a force on it, we got dynamics, and this is some sort of mass. F equals ma is kind of the governing observation of the universe. And forces, hell yeah, we know what those are. We experience gravity, and we have an intuition for what a force is. We for sure do not have an intuition of what acceleration is. Just because when forces balance, you can have constant velocity. We have better association with constant driving down the highway. Hell yeah, we spend most of our time at a constant velocity. It looks like a guy with a hat. Anyway, so we spend most of our time at constant velocity. But yeah, let's talk about acceleration. So I always take a chunk of mass, have its velocity be 0, apply a force on it, and what's going to happen. And then the other thing is that, I would have started this whole video like this, but there's 2 ways to think about, that I like to think about free body diagrams. And I even have an air hockey table. It's pretty sweet. And I should be using it more. But hell yeah, so we have an air hockey table. And I can just put a plastic disc, and let's just say a square, just like a plastic puck, and then I can apply a force on it. And we can do that same scenario where we take a string and then we put our little roller here, frictionless roller, and then drape the string, and then a can of soup. I think that is just a very good, because here's the other thing, is we know like a force will open a door, but what see that's why we don't have a very good intuition for what acceleration is. Because, you know, a door is a chunk of mass, and we go put a force on the door, and then we open it. I don't think anyone thinks that this thing is changing velocity. I think people know that we apply a force on the door and it begins to open. I don't think people also, know that we have to apply an equal force to keep the door from, like, slamming. Or, if there's hell a lot of friction, maybe you're using such a combination of physics there that I bring this up because you do not apply a constant force while opening a door. You're applying a force to open it, and then probably a slowing force, and then like a catching force, stop the door, get through the door, and then applying a force in the other direction, and that's not even a constant force. And so it gets lost that constant forces, especially when, and then most of physics, like literally, friction is neglected. You know what I mean? There's just no friction. And that's an anomaly that we have more of an understanding of friction and constant velocity. Change in velocity is zero. Just velocity is constant than we do with acceleration. And so from this scenario, this thing is going to pick up speed. And this is kind of fascinating because, that said, we had I never got this to work because I just never, as a kid, I never had, you know what I mean? So we had a tree, and then I had a garbage can, and I just had pulleys. They were pretty sweet. So I have some rope, and I have a pulley, and then I just had this heavy garbage can. And what I was going to do is have my brother pull the garbage can full of, like, cinder blocks or whatever. No, I wasn't going to do it. Hell yeah. So I was over here on my skateboard. And I should do this as an adult. Just this. I mean, if you're going to do physics, why don't you do stuff like this? But if this friction is negligible, and you get this garbage can full of heavy-ass stuff to the top, the force, this has mass, and then we have that gravitation, and you could even do gravitational constant. You could say the force of gravity, which is going to be the tension in this rope. The free body diagram right here is taking this garbage can full of heaviness, which does have a mass, and we have an earth underneath us, and then we have a rope. So if this thing is stationary, we got tension in the rope, and it must equal the force of gravity. And that force of gravity is a gravitational constant, mass of this garbage can, mass of the earth, radius of the earth squared. These three things are just g, and it's approximately 10. And the fun thing that I always like to do, since this video is just hella long anyway, gravitational, how do you remember these things? Well, gravitational constant 6, mass of the earth is 6, radius of the earth is 6, you know what I mean? Like the devil's going on here. But anyway, so the radius of the earth is 6 million. Mass of the earth is 6 times 10 to the 24. And even if you didn't know that, you could probably get there. This is 6 times 10 to the negative 11. If you didn't know that and this is obviously squared, and this is the same thing as 6 times 6, and then 10 to the 6 squared. Squaring. This you could break up as 6 times a million. Oof. And hell yeah, and that's going to be 6, and then that's just 10 to the 6. We have to square both of those. That's the same thing as squaring 6, so we're going to have this 6, these 6's cancel. All the 6's cancel, so who cares? That's how you get the 10. From a lot of 6's, you get the number 10. So all your 6's cancel. And then you have 10 to the 6 squared. So you got 10 to the 12 down here. 10 to the 12. It has to cancel this, but leave a 10. You know what I mean? So I need another. I mean, to cancel that, I would have to have another 10 to the 12. But to this would have to be 10 to the 11 down here, and that's exactly what this is. 10 to the negative 11 upstairs is 10 to the 11 downstairs. 10 to the 11 downstairs plus 10 to the 12 is 10 to the 23. And so, hell yeah. And again, that's a fun way. If you've opened up your statics book but don't go over this equation and just get that intuition, I think you're just missing out. Especially when you just see an mg on the page. I don't know. I just think you are, because then you can easily take this force of gravity concept to different planets and have some fun with it. Anyway, so all the 6's cancel. 10 to the 24 divided by 10 to the 23 just leaves a 10 to the 1 up top. Hell yeah. Alright, so back to the whole reason I went over this is that we have a constant force. If I take this soup can right here on this little plastic puck on the air hockey table and I drop this soup can to the floor, it's going to apply a constant force on that puck. And that puck is made of mass and it's going to travel across the universe in this direction. And F equals ma says we have a force on a mass, and we're going to have a change in velocity. So this was at rest. Velocity was 0. But it's going to, every second, it's going to increase in velocity by this equation. So rearrange this equation. You would have acceleration as force divided by mass. That's going to be that force of gravity from your gravitational equation divided by the mass of the puck. And when you do that, obviously this mass of the puck just cancels out. So gravity, mass of the garbage can, or mass of the puck, don't matter. Mass of the Earth divided by the radius of the Earth squared divided by the mass of the garbage can. So hell yeah. And that acceleration is just what we call g. So this thing's going to accelerate, and so I just bring this up because this force is constant. I think that's the reason why I brought that up, and it's very difficult to visualize a constant force. Oh yeah, hell yeah. I brought this up because free body diagrams typically are free. You have some sort of mass, and I just never got this explained to me. It's just like, cool, this is a free body diagram, and you do have this word free in here. And so that's why I came up with, hey, you can do this. You could do this experiment on an air hockey table, and you could also do this experiment in outer space. So, alright, hell yeah, because when I was driving home, and the first thing I thought about this problem from a free body diagram perspective is that the weight of these are negligible, and there's a lot of problems like this. Like the forces just way overwhelm the actual, the weight of the structure. You know what I mean? The forces are going to be so much bigger than the structure weighs. Especially if this is 3D printed out of plastic, it might weigh ounces, and you still might be able to hold body weight on this. That'd be pretty incredible. And so we can analyze it from that perspective. But even just driving home, from a free body diagram perspective, this is something you're not going to just visualize. You're not going to visualize this thing just floating. And because this experiment obviously is done on a horizontal, the Earth is underneath us. I mean, it doesn't have to be. Like, this problem can be done because the mass is negligible. This problem can be done in any configuration. You could do this problem vertically this way, and it's still the same exact problem. You could do it, you can't do it this way, you know what I mean? Well, you could do it this way, because this is a roller force. Like, obviously, if there was weight to these members and no other forces, it would just collapse or fall this way. But because we have some sort of upward component, we're chill here. We could do this problem upside down. And, nothing would change. And so from this free body diagram perspective, especially when I knew that the forces in the members were negligible, I just think of things just kind of floating. And I even think of all the pin connections in these. Also, until forces are applied, if this force isn't applied, And all these masses are negligible. All these pin connections are just floating in here. The second we pull a force on one part of this, sure, then you're going to get loading, and we're going to take a look at that. Alright, so sweet. So if I just said everything is just loose and all the pin, without this force applied, everything is just loose, that is the same thing as this thing just floating in outer space. And that's the same thing as it being flat on an air hockey table and just kind of being elevated. And until we apply a force, everything is just floating there. And so that's why I always start with a chunk of mass and then apply a force on it, and for sure F equals ma. But then you have this scenario where, yeah, if I apply this force, this thing, and with a velocity of 0, is going to travel this way and accelerate, keep speeding up as it goes across the universe that way. And then from a free body diagram perspective, like what comes first, the chicken or the egg? Because you can set up an experiment like this, and then what you're going to notice, I always do kind of an eyeball on this, especially with free body diagrams, is that what we notice is that we don't have any movement. We've identified mass, like all these things, even though their masses are negligible, for this we still have to say they are mass. From my perspective, I would lose my mind if I couldn't say this thing is, made of mass. There's mass, there's mass, there's mass. Because F equals ma. We have a relationship between identifying mass, applying a force on it, which we're pretty intuitive with, and then seeing from observation, do we get acceleration? And that's why sometimes with problems where mass is negligible, you have to start with the applied forces. I think when problems have mass in them, I think it makes it more intuitive, where you're just like, hell yeah, every member has a mass, and I guess it's you know what I mean. I think I've only done the integration once in this year, once total of like. Well, this member, yeah, we put the mass at the center of mass, but I need to do the integration more that, hey, every little molecule on this thing is a chunk of mass and is being equally pulled down a small amount towards the center of the Earth. The Earth is so large that the angle towards the center, this direction to this direction, this angle, these are basically vertical lines, yeah, it's kind of interesting. And those are equal to the total mass, the little m's times g. That's just equal to putting that weight at the very center, the center of area, center of mass of the object. Alright, so I went over that because if you do have a system with mass and you have an Earth underneath us, then you have a force on that mass. Because even if you're just standing on the Earth, like you are no different than a chunk of mass, and the Earth is underneath. So we can identify a force. And it's on a mass. So F equals ma says that this should be accelerating. You know what I mean? And then, but from observation, like I'm not moving towards the center of the Earth, neither is this block of mass. So then what gives? Yeah, I don't think this is so obvious. I think it's always good to, to do this, to be like, well, there has to be an equal force in the opposite direction. You know what I mean? So that's just, there absolutely has to be. Like because if you take something in outer space like a mass and apply a force on it, it is going to accelerate. If you apply that same force on the mass of something floating in outer space and you see that it is not accelerating, change in velocity is 0, then there must be some other force. Even if you don't know what the force is, you know what I mean? But there has to be some other balancing force in that direction. And this force has to equal that force. Alright, hell yeah. I'm going to go over something I haven't gone over, and I'm just kind of experimenting with this. I think the smallest chunks of mass that you can imagine is maybe, you know, like the nucleus of an atom. So if this is an atom, you know, we know that they have electrons, and then the actual mass part is pretty centered, and the electrons are hella spaced out. But I'm just going to always draw like two little atoms, you know what I mean? And so obviously, I don't know what they would be. I would just think they're just iron atoms, because iron is an atomic element, and so you'd have a bunch of neutrons and protons. Like obviously, this is a horrible representation because like those would be your mass clumps of neutrons, and then your electrons would be hella, and this distance would actually be pretty huge. That said, like me visually, I'm still just going to, I guess I'm just encapsulating that whole atom thing as just a couple circles. So hell yeah. So and especially for material mechanics, I don't know. I think it is useful for me. The smallest sub-element that I like to think of is one atom of iron, and hopefully iron's an atomic. Sometimes I never know what the hell's what an atomic element is. I think Fe is iron, and I think that's on the atomic chart. Booyah. And so from this, I can tell you something cool. Because let's say just physically I was able to prevent this iron atom from moving. Okay? And then this iron atom is next to it, and there's just an electrostatic force. Iron, they just kind of, typically iron is just in one of the electrons is just free. I think it's just one. I don't think it's 3 electrons. It might be 3. It might just be 1. But it has a free electron. So iron is just has an electron that's just, you have these sea of electrons, and I guess they'd be negatives. So yeah, it's kind of an interesting electrostatic force. But anyway, so you still have an electrostatic force that holds these two together. So they want to be together. If you had 2 of them right next to each other, bonded, you know, it's definitely, hey, that's your smallest chunk of iron. Anyway, I was gonna say, but yeah, I want to say the word steel, even though it's just because steel is basically 98% iron. So you can just think of steel as, you know, in steel there's going to be 2 iron molecules next to each other. So that's and I think. When you talk about something in subatomic elements, I think it, for me, it's useful to talk about it in materials that actually exist that we use in everyday life. So I'm just going to call this steel as well. Anyway. Alright, so the wild thing is if I'm able to fix, I don't know how I'm going to do that, I would just pinch it in a device, this iron atom, and I put a force on this one through its center. And that's the other thing is like on, hell yeah, I just need to get to it. But if I apply a force on this one, all that's going to happen is this atom with that force being applied is just going to spin around this fixed atom. So if I'm able just to like pin this atom into outer space, put a force on this iron atom, it's going to require so little effort actually as well. So like there's hardly any resistive force to take this atom and then spin it around. And then the other aspect is, especially from the electrostaticness, is, and I'll have to ask my brother about this, but if I do have an atom, I can only apply forces through the center of it. I can apply a compressive forces, a tension force. I can apply an individual single force. But it has to be through the center. The other aspect, you can't take one atom and shear it. You know, you can't grip the electrons and start to shear one atom. And I think that's useful because, especially because a lot of statics leads into material mechanics, is And I think why I'm doing this is because the next thing we talk about is the sum of the moments. We have sum of the forces. We just talked about that if you had this chunk of mass, apply a force that way, observe that it's not accelerating, there must be an equal opposite force that way. Also, if I had a, let's jump back because we need to talk about vectors. And this is an interesting property. If I have this mass and I apply this force, we'll call it Fx, and I see that it's not moving, I have to have a force Fx in this direction. If I see that I have this force Fx in this horizontal direction, and I want to stop it from accelerating, you know what I mean? If this whole thing is just zero velocity, and then I instantly apply a force this way, and I think I'm going to apply a force in this direction, some force in the y direction, that ain't helping. You know what I mean? This thing is still going to be traveling across the universe as if this force wasn't even, like, it doesn't even exist. You know what I mean? So that's fascinating that if I have a chunk of mass with a force, Fx, and starting with zero velocity, and then applying this force, we're going to be accelerating. F equals ma. The acceleration is the force x divided by the mass. We will see that acceleration. If at the same time zero velocity on this, I apply both these forces, guess what? We are still going to have the same acceleration, Fx divided by m, in this direction. We're also going to have a component this direction. Ay is Fy divided by m. And so that, you can never go over vectors from the basic level, because that's something that you'll probably forget. Everyone says some of the forces in the y, some of the forces in the x, but it's because vectors, because forces can be considered vectors, and vectors from a mathematical perspective can only have certain properties where this force is Alright, I gotta use my words, choose my words correctly. So this force cannot be balanced by this force because it's perpendicular. Because these two forces are perpendicular, this force cannot be balanced by that. You know what I mean? And then, even if you had this, a force in the x, and then you just had a slight angle this way with a force in the y, or just this force F. Sure, this has two components. Now, this component can balance Fx. So if I say this is F2, and this is F2x, F2x can balance Fx. But you're still going to have this residual downward force. You know what I mean? So sure, you can prevent you can have no movement in this x direction, but if this is the only two options you're given, if you apply a force Fx, and the only way that you can resist it is to apply a force at this angle. Well, you can prevent any movement, and if this thing had an initial velocity of 0, you can prevent movement in the x direction, but you are going to have an acceleration in the y direction. You're going to have a net force in that y direction. Alright, hell yeah. So let's go back to here and kind of tackle the moments. Because the other thing that you can't have so if we do have chunks of iron atoms that are connected in like a rope, like this, it will act as a rope. If I go ahead and pinch this one, and we're at the top of a cliff, this will be in this position. It won't hold itself up. So this will not maintain rigidity because of this. I think it's useful to talk about these iron atoms as something that don't want to be pulled apart. You know what I mean? So if they get pulled apart, they can only be pulled apart so much, and they want to come back together. So it's like they're attached by a spring. The other aspect is that you can't push them together too much either. You know what I mean? So they don't want to overlap a whole lot, and that distance that they actually overlap and get pulled apart are actually going to be the same. For steel, that's wildly the same distance, and I think that's fascinating. And so that also shows that these the masses are really small and in the middle, and these distances are very large. So there's your masses, and the distance that you can separate these is if this was 1,000, if each iron atom was 1,000 millimeters, and this is from material mechanics, is that the linear elastic range, you can only separate these by 2 millimeters. And so what we have is that this distance from center to center is 1,000 millimeters. And this distance can increase by 2 millimeters. But that's it. And this distance can overlap and decrease by also 2 millimeters. So plus or minus 2 millimeters. And this is the electrostatic forces that are holding these iron atoms together. Cool. So now I'm going to show why things, how you can have it, because this is not rigid. Like that's, I mean, I guess it's because this would be all sorts of floppy. And by definition, this is not rigid, because if I fix this can just spin around that. And the definition of rigid is that, like, if I have this bar as rigid, and we break it up into 3 squares, if I rotate this square to a 45, so we're going to rotate that square to a 45, it says every other piece of this rigid body follows along. I don't know if that's the actual definition, but that's fairly close to the definition of rigid body. Where if you go back to this and turn this into a square and then this one into a square, what we just said is that we can rotate this square all around. You know what I mean? And I don't know how you would visualize that. Whether you would visualize it like rotating around like this. You know what I mean? I don't know if this would actually rotate 360 while it rotates around, but hey, this one's fixed, and you have all sorts of difference compared to the definition of a rigid body. Okay, so you have to have at least 4 of these. So that's kind of my little approach of visualizing this, especially because this is such a good way to visualize things in material mechanics, because this brings up the idea. I think it tackles 2 things. I think it can tackle some of the moments, and then also what we talk about as shear forces. And shear forces seem, I mean, to me they still sound made up. But here's the graphical definition. And we're still going to say that a force can only be applied through the center of an atom. You know what I mean? So we can have any of these lines of action, but the force has to be through that chunk of mass. And that's because electrostatic, you know what I mean? That's where all the mass is, and we still have, well, don't quote me on that, because obviously we have electrons flying around, and but I think I asked my brother that, and he's just like, and I thought it sounded legit, that you can't take an atom and apply a torque to it. I don't know. I don't think you could, but I could be wrong. It makes me think that aren't photons, don't they have an angular momentum? Isn't that a torque being applied to something that's massless? I don't know. So I mean, So there's a lot of this that's speculative, but from a macro scale, I think it can be fairly decent. So if we say that we can only apply a force, so what we're going to do is we're going to apply a force in the definition of positive shear. And so we're going to apply an upward force here, and we're going to apply a downward force here. Now cool, it looks like these are balanced. I mean, it seems similar to applying an upward force there and an upward force there. You know, our sum of forces in the y are 0. You know what I mean? So what gives? Oh, this is cool, because I can go back to this one. It's like, well, couldn't we just do this with 2? You know what I mean? Couldn't I put an upward force here and a downward force here? Sure, but if I said I have to apply forces through the center of these things, like this thing is just going to spin nonstop. We're going to have a torque about, you know what I mean? These two forces are separated by a distance. That's the definition of a torque. That's force times distance, or a moment. Force times distance. Also the definition of a couple. Force times distance. 3 different ways to kind of relay the same thing that's going on. And from a dynamics perspective, we know that this is going to, if we have a torque, torque is going to be proportional to angular acceleration. So this thing, how we say in angular world this velocity is stopped is that we say, hey, this angle, let's say it's a theta, and theta is 0 degrees. That change in angle that change in angle per second. So we have a change in angle per second is 0. You know, that's not well, that's the definite angular acceleration. So we have oh yeah, because this thing could still be spinning with an angular velocity. So we could have a change in angle per second. You know, just a constant change in angle per second. You know what I mean? So let's say it's just 5 degrees a second. So we have that constantly spinning. And if that thing's just floating in the universe, constant spinning, it'll float like that way forever. So I think that's also a good... It's also, yeah, so kind of bringing in some dynamics as well. Hell yeah. But if we wanted... But I always like to start things from... I think it's easier in your head to start things from 0 velocity. So I'm going to hold these two atoms fixed. I'm going to apply these forces. And then I'm going to be like, now what? Well, that means that we're going to not only have... we're not only going to pick up some angular speed... but the angular speed is 0, so we're going to pick up some. So that's going to be a change in angular speed from 0 to some number. And that's going to keep increasing. So this thing is going to start to spin and then spin faster and faster. So just even using the words stopped, start to spin, spin faster, that is just because angular acceleration is a mouthful to say when you just had to say acceleration for the other one. Now you have to put on this adjective angular. But it's spinning, and it's spinning. It started from rest, it started to spin, and it's spinning faster and faster. And it'll just keep spinning faster if you're applying this torque. So that torque is proportional to alpha, which is angular acceleration, which is omega divided by s, you know, or change in omega divided by change in time. And change in omega is change in angle divided by change in time, divided by change in time. So that's cool. And so if you have that, when you just have two things, you have a force this direction and a force downward. If you wanted to prevent that spin, well, this is causing a moment, you know, in this direction. You have to apply two other forces that are opposing. So the only way to do that is to apply a force this direction and a force that direction. And then maybe I'm losing my analogy, but I mean, that's cool. We call those F primes, but I mean, that's literally, there's nothing different between a chunk of mass that has a force and then just opposing force. Like, this is the only thing we can do to keep this stationary. Just treat these like individual chunks of mass floating, identify one force, match it with the other force. But if we have a grouping of 4 atoms, we don't have to do that. I don't have to come in here with a line of action and put a force here, or a line of action and put a force here. I'm able now that this is a, kind of more of a 3D structure, where this was kind of just a linear structure, is I can, and these forces are causing a positive moment. I just need a negative moment, and I can apply that on these lines of action. So I'm going to apply a force here, and then a force here. So this is going to be F prime and F prime. All these distances are going to be the same. And so, the torque. Alright, hell yeah. So what we can see from this is that if I apply this upward force, I have to apply this downward force, so these have to be equal. These are separated by a distance, so it's causing a tendency to rotate. That's that value on torque. And that tendency to rotate has, because this, we're saying that this is, we don't see any motion. We don't see any angular acceleration. Therefore, this torque has to be equal. You know what I mean? That has to equal, let's say T prime is this couple. And so again, a definition of a couple is 2 opposing forces separated by a distance. And that's also, can be classified as a moment or a torque. So couple, moment, or torque. Alright, so I am going to show, like, I said if I had this and I apply a force right here, it's just going to spin about this. So why, if if I have this fixed? So why, if I have this and I fix these two, so these two are fixed, and then I apply a force here, why all of a sudden does this not just spin? Like, what happens to this scenario? Yeah, so basically that's the question. And it's because I just mentioned that electrostatically, these don't want to, it takes force to pull these apart before, let's say, they rip apart, and it also takes force to push these together. Seems like you could push them together infinitely, but we're just saying that there's a point where in material mechanics you can elastically pull things apart or elastically push them in. After that, either it becomes an inelastic, or it's usually at the point where you design to stay within that elastic range, because you might get failure on compression or tension past that. Cool. So that's the electrostatic properties of metals, because you have atoms and they're bonded together. I basically think from electrostatic perspectives. I mean, if I'm not saying that 100% correctly, still I think it's in the ballpark of cool, makes sense. Now explain why this spins and this doesn't. Why this can maintain rigidity. And so these two can't. So again, those two right there, those bottom ones are just like this. This has a tendency just to spin effortlessly around. So really what's happening is that this one is just pushing into this one, and it's this one that and then this one, like, let's take a look at these two. This one also can easily spin around this. And if that one did, so this top one, if it started to spin around, it would then be kind of in a higher location. So, and that's the thing with circles. If you have a big enough circle, if you start from here and then just move a short distance, you literally moved in a vertical direction. And so that's what we're showing. And because these distances are so small we're talking about, so I'm going to move in an upward direction, starting that spin. So this one's going to be up here. So what I'm going to show is that we have electrostatic forces between all of these. All four are electrostatically kind of connected. And so what we just did was move these two farther apart. These two didn't get farther apart. This one actually went along with the other one. You know what I mean? So the new location is up here, and then this one's right there. So these two didn't get farther apart. These two didn't get farther apart. These two didn't. These two didn't. But these diagonal ones, hell yeah, they got farther apart. And you can also say that these two got closer. You know what I mean? That might be a little bit harder to see. But for sure, these two got farther apart. And so that's kind of the definition of why this is a rigid structure, because as these are getting farther apart, we're having a force to restore that. Whereas if you just have this and I apply a force on this, it doesn't really, there's no restoring force. You can just easily spin it around this fixed atom. But yeah, so that's why all you need is 4, and you get that to happen. And it still requires this upward force to be balanced if you have this upward force, because this is the definition of shear. If you know one of the forces, shear forces, you know all 4. You have a downward force. This causes a couple, therefore you have a force this way and a force this way. Hell yeah. And as a, if we're saying, and this has a tendency to get into this shape, and that's positive shear. And so we do positive shear by saying we have on this face, we have an upward force, a downward force that's causing this moment, so we have to balance it. So we have a force this way and a force that way. And I think the easiest way to graphically represent this shape is to fix this location. That location is fixed. And then to see what these two sides do. So I'm going to say that this side moves up. This side moves over. And the definition of pure shear is that these lengths don't change length. Well, I mean, the angles are so small, but yeah, these lengths don't change. So we have, anyway, what did I say? Fix this point. Make this one go up, this one go over. These two have to be at the same location, so we box it in. I call it box it in. And then you can easily draw this shape. Just kind of connect those dots. And this is the shape for positive shear. When this force is up, and this force is down. I'm just going to use F because actually this is actually this force right here causes this to rotate this way, which is the definition of negative shear. So that is negative shear. But check it out. These two forces cause a positive shear. The positive negative rule, whatever you call that, is going to be positive when it tends to rotate an object. But that's bizarre. Okay, so positive shear is only the, whatever you call it, the positive negative sign convention for shear is only associated, and it's typically with beams, because beams are this way. And when you take a chunk out of a beam this way, it's only for vertical faces. If you have a vertical face that has a shear force that tends to rotate it in the clockwise direction, which kind of goes against the counterclockwise convention, so keep that in mind, this is going to be a positive shear. And that positive shear has to be associated with over here, and then these would be associated with that. And this shape, if I started here, so let's do that one. So I'm going to take this shape, fix it right there, This length goes down. This length goes over. These two spots have to be the same, so box it in. And then we get this shape, which, if this angle widens, is called negative, that's negative shear. And this is the angle that we associate with shear. And so this is positive shear, this is negative shear. And that was, and to get this, that was a positive shear force caused negative, negative shear strain. But if you take that same element and look at the top two faces, well, those forces are causing a tendency to rotate counterclockwise. So that's the deal what gives. It's typically when dealing with beams. And the reason we do that is because the equation associated with shear, as an equation, lines up with the equation for moment, which lines up with the equation for angle, change in angle, which lines up with the equation for deflection. And all those can be represented graphically in the same, you know what I mean, with the same sign convention. But it is a little bit, yeah. So I'll just enough said on that. All right, so maybe that was just a long way to, talk about some of the moments, and I guess, it's easily just classified as if I have this, if I have a force here and a force here, hey, this thing is going to spin. So this is for sure going to spin. The only way to stop it is to put forces, in the, in the direction of the other forces. Whereas, if, most structures are kind of, three-dimensional, or, so if I have 4 of these, and I put a force there and a force there, sure, these have a tendency to spin this thing this way. And if it's a statics problem, I mean, if I see no spin, no motion, no rotation, then there must have been a balancing torque. So if this torque is this way, there must have been a balancing torque. I could put that torque here and here, or I could have just put that torque here or here. Both of those, whether this is F prime or F double prime, two different scenarios, and that still fits this idea that if I can only put the force through the center of these masses, then those are the locations. And you know what I mean? I could actually, yeah, that's not true. You know what I mean? So it's, if I have this force and this force, this is going to cause a rotation that way. So I need a countering force this way. That could be this. This could be F prime there, and then F prime at these diagonals. These diagonal distances, are going to be different. And so these forces might be different, but the torques that they apply, the torque due to these forces are going to be the torque due to those forces. So if I say this is distance d and this is d prime, I have FD is the couple associated with these two forces separated by a distance is equal to F prime d prime. Hell yeah. All right, hell yeah. So that's my intro. And well, let's do one more thing, because I think when I solve this problem, I kind of want to make 2 videos, this to be the long as one. And so the other aspect of these problems is you can look at this whole structure as a rigid, structure where you have, just this applied force on it. We have a force this direction, and then we have 2 forces here. So this is where I need to do more of just kind of sizing these up. Because this force can only resist an upward force. You know what I mean? If something if this is a grocery cart and you pull on it, this whole roller assembly is just going to go that way. Like, it can't do anything about it. Like, if you see that this is getting pulled that way, this roller thing ain't helping. You know what I mean? So it's just like, who's doing all the work? You know, when you're driving by the people digging the hole on the highway, it's the guy digging the hole. You know what I mean? So, hell yeah. So if I have a force this direction at point A, this thing ain't doing nothing. You know what I mean? Okay, cool, that's said. And, hell yeah. So that's kind of the first thing that I'm going to notice, is that I do have a component of this. So this force can be broken up into two components. And you can do this parallelogram method anyway. You know what I mean? If this is the vector, you can go that way and this way, or this way and that way. Sometimes it's useful just to show the two components from A. Sometimes it's useful to show this and that. I don't know. It depends on what your fancy is. Because obviously this is a right triangle, or this is the hypotenuse. So if you do it this way or this way, you can easily see that. Where if you just did this, you might not see that that's part of a right triangle. Okay, cool. But, so, okay, hell yeah. So this force P has a px component and a py. This px component, this roller ain't helping that. So, therefore, we know that this, just by, so we haven't even done any equations. I mean, we kind of know that Newton's laws say, hey, this is just a big chunk of mass. And so, to make a simpler problem, this is literally, hey, we have a chunk of mass like this. I'm going to put a force on it, px, and I know that I can put this force down here, but that ain't helping. And so the only other place that I can actually apply a force to balance is here. So I'm going to say f of x is equal to px. So there you go, first equation. Px is equal to f of x. Or vice versa. F of x is equal to px. And that literally is a part of the force, the reaction at, of what we want to know. All right, hell yeah. We do have, and if we have, let's just kind of move on. Oh, hell yeah. You know what I mean? And then we get to use some of the moments, like, I didn't think we could. Yeah, it's kind of interesting, but all these problems are basically, finding global equilibrium if we have a couple points, and if you can't, it's usually going to be a indeterminate, problem. But yeah. So this one is still within the realm of like, hey, we have one force here, we have an fx, and we have a fy. And so, back to here, and we have an EY. So we have an EY, an FX, and then we have an FY. I know that these two are going to be equal, so hell yeah. I know that, what else do I know? Oh, yeah, and I have this. I'm just going to say this, and that's the direction of this, and this is a PY. Yeah, and this EY is somewhere right here, EY. Alright, hell yeah. So now we have to look at the sum of the moments, and for whatever reason, I don't know, it's not 100% intuitive to me. And so I'm going to go back to kind of, something in outer space. And we just have this floating in outer space. And the sum of the moments says you can pin this thing anywhere. I'm just going to, if you can just imagine putting a thumbtack into, this object, and it's pinned against the backdrop of outer space. And so if I apply a force here, well, hell yeah, it's pinned right there. It's going to spin like that around that point. And it's going to do so because of this distance. Cool. And so the only way to keep it from spinning, and this is a case where we don't have like a couple. We just have a direct torque. Definition of torque is R cross F. And we have a distance perpendicular to this force. That's kind of what the cross product would be saying. Because if this force was directed through that point, well, you know what I mean, then there would be zero torque. And if this had a component this way and a component, well, I mean, if it had a component in this direction as well, you know, if it had perpendicular components this way and this way, it would, I don't know what the hell I'm saying, but anyway. So yeah, you got a force here. Sometimes the geometry kind of gets me. So let's take a step back. And it's perpendicular. This is going to cause a torque, and if we're pinning this thing, it's going to rotate proportional to that torque. If we're seeing that this thing visually is not rotating, there must be an equal and opposite torque. So this torque would be a positive right-hand rule. We must have a negative. And so we could get that. We could apply the torque right here, smaller distance, and let's say this is an F prime, and then here's our distance D prime. And so, therefore, you know what I mean, this torque has to equal that torque. And when we do that, let's say this distance is, well, I don't know. I don't want to get this too confusing, but we're just going to say this distance is 10, this force is 10, this distance is 1, and so this force would have to be 100. Cool. All right, not bad. And then we have some dimensions on this. This whole thing is 11. And so let's say I pinned it oh no, this is good. I mean, we have to do this for a starting point. And then about this, and I guess let's just call this an actual pin. And this thing is still floating in outer space. I'm putting a force of 10 here, a force of 100 here. At this pin, I must have to have a force of 110 to keep this thing balanced in the y direction. Therefore, some of the forces in the y are balanced, and then some of the torques about this point, we've already done that. That's where we started with. Some of the moments about that pin, I'm just going to call it O, is 0. So that's where we started from, and there's no wall here. This is just floating in outer space. But now we can pick any point on this. So let's pick a point right in the center, and we're going to say some of the moments about the center are 0. And this is true because this thing, from observation, is not moving in the y direction, the x direction, or rotating. So therefore, it literally is just stationary. It doesn't matter if I pinned it. Like this whole idea of pinning something is kind of irrelevant. It was relevant at this. This had to be a literal, you know, pin where we could have rotation, but then that pin also had a force. Cool. And yeah, I mean, this video is long enough, but that was part of this 3/4. There's one on 3/4 members, so let's read that one. Because yeah, because that's what I was thinking. It was just like this 3/4 member got me thinking about this, is if there is no rotation, it's like, well, do all the resultant forces meet at a point? And I think it's only if you have 3 resultant forces, which we do. We have a resultant force here, a resultant force here, and a resultant force here. This whole thing is this whole object is a 3/4 member. You have a member, and you have 3 different forces on it. Due to some of the moments, I mean, if this thing is a statics problem, all those forces are going to meet at a point. And so that is fascinating. And so it's interesting to me is if you Yeah. I don't know, could you... Yeah, anyway, so let's read this. So it says 3 force members. If a member is subjected to only 3 forces, it is called a 3-force member. Moment equilibrium can be satisfied only if the 3 forces form a concentric or parallel force system. So therefore, if you had 4 forces, it doesn't have to form a concentric. So that's the definition of 3-force. If you had 2 forces in a moment, this does not apply. If you had 3 forces and a moment, this does not apply. So it's just kind of fascinating, doing the same thing for this as we did with the 2-force member. If it says 3-force, that means 3-force, no moment. 3-force, not 4-force, and no moments. Cool. All right, so you have this concurrent or parallel force system to illustrate. Consider the member subject to the 3 forces F1, F2, and F3 shown in figure 521A. If the lines of action of F1, F2 intersect at point O, then the line of action of F3 must also pass through point O so that the force satisfies the sum of the moments about point O is 0. However, we just did this where we have 3 forces and, they're all vertical. And so what gives? As a special case, if the 3 forces are all parallel to each other, figure 521b, the location of the point of intersection, this point O, will approach infinity. So hell yeah. So that would be a good that would be a good advanced problem to be like, hey, where is the concentric point? What would we call that? Let's see what they call it. They even call it concentric? Probably not. I probably just made that word up. So 3 forces form a concurrent or parallel force system. Oh, yeah. So this one's concurrent and this one's parallel. See, I'm just, some of these big words and stuff. Anyway, so hell yeah, a concurrent. So a good question would be like, hey, we have 3 forces acting on this member. Like what is the point where they intersect? Because they're concurrent. Because they're a concurrent force system. Alright, sweet. Hell yeah. And, cool. Oh yeah, we're talking about sum of the moments. So that's kind of where we're at. And, yeah, we're going to sum the moments about point C. Okay, if this whole distance is 11, this distance is 1, halfway is 5.5, so this is going to be 4.5. Cool. So, yeah, let's just do this fairly fast. Is that this 110 is going to be a positive moment. 110 times 4.5. That's going to be positive. Hell yeah. This is going to be negative, and it's going to be 100 times 5.5. So it's negative 100, 5.5. This moment is going to be positive, plus, and that's going to be 10 times 5.5. Let's see if I can do this without calculator. Probably not. This is going to be negative decimal point 2 zeros, 550. This is going to be positive decimal point 1 0, so we have plus 55. So hell yeah, so this one's going to be about 500, negative 500, but we're going to subtract 5 more, so negative 495. How would I do this one? This is the same thing as 110 times 4. That's going to be 440. And then 5 times 110, which is going to be 550. But that's just going to be 55, and this is 440. I'm trying to use my calculator less, so booyah. And we got 55 plus 440. That's going to be 495. So 495 minus 490. I even forgot what we were doing. Hell yeah, some of the moments are 0. So we have a check on reality that we chose this point to pin. Like, obviously this is just an irrelevant point, but I think that's useful when knowing that you can have an object with a bunch of forces on it, and the torques are 0. And that means that you can theoretically put a pin in that floating object in outer space. Again, free body diagram means that this chunk of mass is just floating in outer space. We're applying all the same forces as you would on Earth to that floating system, and it's not moving in the cardinal directions, and it's not rotating. And so the idea of pinning it is maybe dumb, but you know what I mean? You're just like, well, I'm pinning it, and I'm wondering if it's spinning about that point. How I would know if it's spinning about a point is if the sum of the moments about that point are not 0. And it was cool to start backwards. What we did was we pinned a point right there, had this force have to balance that force. So we started with sum of the moments about that pinned point had to be 0. And then once we found that this force had to be 100 and this force was only 10, then the light bulb went off and you're just like, whoa, we just, like, obviously this thing, you know, would be traveling across the universe that way if this force was 100 and this force was 10. You know, the thing would be moving that way. We know it's not potentially from observation because we did this experiment on the Earth. We set it up. And so the only way to make it not move is if there's an equal force in that y direction. But that was useful, starting with the moments first and then figuring out that there must be a force in that direction. Cool. All right, so hell yeah. And for problems like these, well, for sure you're going to pick a point where when you sum the moments, so yeah, so like right here, we got to the point, and let me throw in some more light. Alright, hell yeah. I mean, we didn't get very far, we just said that, hey, this has to have a px component, this don't. So this f of x has to equal px. Done. I still don't know either of these two forces, so what we're going to do is sum the moments about E, or sum the moments about F. If I sum the moments about E, I know this force causes a moment 4 times f of x. I know this px causes a moment 4 times px. I know this force py causes a moment py times, or 6 times py, distance times the force. And then I just don't know what Fy does. You know what I mean? So that's a positive moment, 3 times the force. And I can just kind of assume, you know what I mean? Can I even figure out what direction this is? Let's see. Because if I'm pulling on it this way, this is going to pull back. If I'm pulling on this way, and this is, sometimes you have to look at pivot points. Like if this is, especially with the sum of the moments, if this is a teeter-totter and I'm pulling down, like if you're a person on this side of the teeter-totter, like, and this doesn't exist, this thing is just going to rotate about this point. And the only way to make it not rotate is to have a downward force right here. So I'm assuming that if I'm pulling this way, and because this force in this direction has nothing to do with this force. You know what I mean? So that's also, keep that in mind when it comes to forces as vectors. Where if you do have a force in this direction, it's really irrelevant to its component in that direction. I don't want to eat my words here because we're going to be talking about two force members, and when, you know, if it has to have a vertical component, I don't know. I'm just going to stop saying words. So cool. Alright, so I just showed from a teeter-totter perspective, a downward force is going to cause this to go up. Oh, yeah, I wanted to know if, from a teeter-totter perspective also, it could rotate around this point. So if I pull this direction, just from a yeah, because I was eating my words there, saying that this force has nothing to do with this Fy, That's not true. Because if I have this pin right there, and I go and then pull on this point A, this is going to cause this whole thing to rotate around E. And then if I have to only have a force in the F direction, Fy, it would have to be downward. You know what I mean? Because if this is rotating it this way, I would have to have a downward force rotating it the other way. So I'm glad I didn't eat my words, and I also, you know, I think we're now definitive that Fy is in that direction. You know what I mean? So f of x is in that direction, Fy is in that direction, Px, Py. Cool. And now I know my two forces in the y direction are down, and so Ey has to be up. And I probably could have got that just from the actual thing. If I'm pulling down on this, you know what I mean? And this is the contact point right here. It has to be up. And it's just fascinating that this is down as... wait, is that even right? I think I'm thinking of it as yeah, that's what trips me up, is like, what are we talking about? Like this rigid body could just be this card. I'm pulling it this direction. I'm holding it, you know, it's going to pivot there. I don't want it to rotate, and then so I'm pulling down on it at the same time. But what trips me up is the equal and opposite. Like, pulling down on this means that something, or like this is pushing up actually on something. You know what I mean? Same thing is if I pull down on this and pivot it right here, and then I have like a wall right here, you know, something to resist. Hey, that's actually pushing down on... or I could say that this is pushing up equally. That's what I was trying to get at. Is if this force is pulling kind of down on this this structure, and we're pivoting about this point, it's going to push up into whatever comes in contact. And so this thing right here, this metal flange is being pushed up upon. You know what I mean? So, which means that the metal flange is pushing down, yeah, down upon this thing. I don't know, yeah, every time anytime I have to deal with equal and opposite forces, I have to take a royal pause. I haven't come up with, you know, too many good ways to just really make that solidified. Yeah, equal and opposite forces. Man, that's brutal for me. I don't know why. Alright, hell yeah, let's try to speed it up, you know, kind of get through this thing, because that was, you know, 2 hours on intro, and then another hour just to get to a global equilibrium, just finding this reaction and then those two. But hell yeah. So from that perspective, you know, we know these given values, the directions, and we just saw... Alright, the juice cut out, but hell yeah, these were given, this force, so we have a px and py given. What do? This is the only force that can resist the horizontal direction, so we know f of x. We could sum the moments about either f or e to find the other value. You could do that twice, but once you do it once, let's say you sum the moments about e to get f of y. Cool, then you know your two y components, these two, have to balance with this y component. And so hell yeah, you did global equilibrium. Okay, and so I said we need to speed it up, but probably not, because this whole point was to use kind of this pin method. Because what I really want to do for this problem is to do free body diagrams of just the pins. And I think that's kind of fascinating, because free body diagrams is like, well, and we just did our first one. The first free body diagram is like, well, you're just pretending this structure is floating in outer space. You applied this force, you applied this downward force, you applied this force in this direction and then the upward force. So because each of these pins can also be expressed as something floating in outer space, let me get, hell yeah. So here's a nice little pin. And then we're going to apply a force on them. You know, if I apply a force this way, well, I know that, so I have a pin there. 1, 2, 3, 4, 5, 6. I got 6 pins. And so each of these pins, I can just pretend are floating in outer space and have a known force on them. Like this pin has 1, 2, 3, 4. 4 known forces. It's got a force this way, a force this way, a force this way, and a force this way. So hell yeah. And these forces can be either, this one can be either that way, or it can be pulling. You know what I mean? This member could either be pushing, or, you know what I mean? Pulling, it could, yeah, however you say it. Push it or pull it back. This member could push or pull in that direction. This member can do that or that. Alright, sweet. And then so think of these pins as a chunk of mass, and then you have forces on them, but they are also by observation. You know what I mean? By observation, they're not moving. And so the forces on these pins have to be balanced. So some of the forces in the y direction have to be 0, and some of the forces in the x direction have to be 0. And these pins are like, you know, they're literally just pins with maybe some grease in them, so you can't put a moment on these pins. And so the sum of the moment about the pin is irrelevant, because if I have this pin here, all the forces are going through this pin. So if I sum the moments, there is no force that's a distance away from the center of this pin. Yep, so there is no moment on the pin itself. That's the other aspect of this problem is, you know, and I'll go over it again, is that if I have this situation where I have a downward force and an upward force, like I said, it's just going to spin. The only thing to prevent this spin would be to apply a moment. You know what I mean? So if I do have an upward force, the only way to resist that upward force is to apply a moment, let's say at this point. If I can't apply any forces between here and here, if these are the only locations where I can apply forces on these members, and I have a force that's perpendicular, the only way to keep this member from spinning is to apply a moment. I can't do anything just by having this pin here. I can pull on this pin, doesn't really matter. I can push on this pin, doesn't really matter. If I pull down, it's going to increase the rotation. And if I pushed up, well, I mean, it could be falling from the sky, but like obviously it's a statics problem where this pin, you know, is rigid, and a tangential force cannot be balanced on this pin. And I don't know, it's just kind of bizarre. You think it's like its structure is just like, why couldn't you put a sideways force on one of these members? Yeah, it's kind of interesting to me. Alright, hell yeah, I'm just going to say it because it's not intuitive to me 100%, you know what I mean? Let's take this member CD. You're just like, and let's say this is a fully rigid, you know, structure over here. I don't know, you know what I mean? And then what I'm going to do is I'm going to take these pins and then push this pin into these two members. You know what I mean? Like, why wouldn't it have a lot of force on it? You know what I mean? If I'm forcing these pins into it, well, it's the fact that this member can still just move about these pins. So these pins, if I did that, if I took these pins at C and D and pushed them into these two members, well, yeah, that's all I'm doing. I'm taking these two members, and if they're rigid, you know, up against, all I'm doing is taking this pin and then pushing it in. So this pin, hell yeah, we have compression in that. And the same down here, as I was saying, taking this pin and pushing it into there. But what doesn't happen is that this member, you know, if I do that, is just chilling out. This member can just free to wobble, and so that I think solidifies for me that yes, a member like these, you can't have a sideways force on them. Yep, and good enough, eh? All right, so hell yeah. So let's try our first one, and kind of from the free body diagram of this pin at A. So hell yeah. So we have this pin at A. I'm going to put a force, Py, and then I'm going to have a Px. Cool. And this is A. I know that I'm going to have this. And we've already, stressed that, hey, this is a two-force member. It can either be in this direction or this direction. Don't know. You got to choose and then see if it works out. And then I'm going to have this member is going to have a component. So AC is going to have a component. And you can do this real big. It doesn't matter how big the arrows are. So there's ACY, and this is ACX. Cool, and you can even go this way with ACX, ACY. And so on our picture, we're going to have ACY, and then we're going to have, and I'm just going to put this one in the positive direction. So we have ABX, and then we have ACX. All right, and so I guess it got busy, but what stands out to us? I mean, we got 1, 2, 3 in this X direction, and we only know, like, I'll circle the ones that we know. And in the Y direction, we only have 2, and I know one of them. So I know that this has to be equal and opposite. So now I know that ACY is in that direction. And, yeah, cool. And so did it. And if I know ACY, this is going to be the trickiest thing from geometry. This was what I was trying to show from, like, the shopping cart. Let's say let's say shopping carts have little sensors on them, and they tell you how much force you're pushing on this bar. And no, they're going to tell you how much force you're pushing in this direction. And it says for normal shopping cart action, you need to apply 20 pounds. But you're applying this at a 30-degree angle, which is effective. Like I said, anything less than 30, hey, this is 0.866. And so whatever you're pushing, 86% of that is going towards this 20 pounds. And so, so hopefully it's obvious that you need to push more than 20 pounds in this direction, this inefficient direction, to get 20 pounds in this direction. Because you're a vector pushing, you have a component down and over. And you need this to equal 20. And then so from a sine-cosine perspective, is if I knew the hypotenuse, I would know, I think it's easier to have a triangle, know your hypotenuse, know this is 30, and be like, oh yeah, sine, draw your angle, this is the sun shining on the sine and cosine, and this is the cosine component. And so the sine component, this length is just going to be the hypotenuse times a percentage. And I always think sines and cosines are percentages. So this is h sine of the angle, and this cosine component is h cosine of the angle. And this is just the percent of the hypotenuse in this direction. This is the percent of the hypotenuse in that direction. Sine of 30 is 0.5, so this is 50%. So that's going to be h times 0.5. The cosine of 30 is 0.866, so that is h times 0.866. Cool. I think it's harder to go the other direction. If I have a triangle where this is 30, and I just know this side, what should I call it? I don't know, like triangle ABC. So I know A, and I want to know my hypotenuse. Hypotenuse, I don't know. And so, like, how do you work backwards? Is like you're still going to use sines and cosines. You're still going to know that this is the cosine component. If I had the hypotenuse, I would say that this is just the hypotenuse cosine of 30. If I know this angle, I still know it's related to the hypotenuse. What I notice is that cosine is always going to be, the cosine of an angle is a percentage, and that percentage is always going to be 0 to like 100%, 0 to 100%, so that ratio is going to be 0 to 1. And it's always going to be typically a smaller number. I mean, if you do have a triangle, it's going to be a smaller than 1 number. So this component is always going to be this bigger number times a smaller than 1 number to get, you know, a fraction of 1 to give you a smaller number. If I know the smaller value, how do I get the bigger value? Well, I take A and I divide it by a small number. Dividing a number by a number less than 1 gives you a bigger number. And so, hell yeah. So that's how I can do this with intuition, is just saying, if I know this, what's my hypotenuse? It's going to be A divided by the cosine of 30. And I think that's one to get used to and just develop an intuition. And I think you develop the intuition first by saying, hey, what are these components? Well, this is going to be the percentage of the hypotenuse, so it's the hypotenuse times a smaller number. That smaller number is sine of that angle. And then so in reverse, if I know this side, let's say, what's the hypotenuse? It's going to be that divided by that smaller number, sine 30, and that's going to give me that bigger number, that hypotenuse. Cool. All right, hell yeah. So all of that just to say, hey, we know what ACY is. It's going to be in that up direction, and it's going to be equal to PY. You know what I mean? So we found our kind of our second one. And if I know what ACY is, hey, I got this triangle. You know what I mean? Hey, we got and this triangle right here is a 3, 4, 5. So we got 4, 3, and 5. And I know that this is the 4 component. So, and I guess, you know, we went through it with angles, but it's still the same. Like, if I knew this length and I wanted that length, I would take this length times a smaller number. So I'd take the hypotenuse times 4/5. And that's the ratio of this length divided by the hypotenuse. So even me, I'm just getting better at being like, well, if I did it my way, I would take this ACY and divide it by that smaller number, that 4/5. You know what I mean? Actually, with fractions, it would probably be easier just to say, hey, this hypotenuse is going to be 5/4. But I don't see that 100%. I like to I don't know. You know what I mean? How can we do this fairly easy? I mean, we have you basically have you also have ratios. You know what I mean? This is the ratio. So if you have the hypotenuse, I don't know, divided by ACY is equal to 5 divided by 4, and then just solve for your hypotenuse. That's 5/4 ACY. Get the ACY over here. So yeah, it's good to do things in 3 or 4 different ways just to make sure, I don't know, you got the intuition. But I do like that, hey, if I think it's real, you can't go wrong by saying this is the smaller component. This is a right triangle. I want to know the hypotenuse. It's usually the vector that you're trying to find, let's say. And you know the components. And so I know that if I know this component, this vector, AC, has to be bigger. And so I must multiply ACY by a bigger number. You know what I mean? Or take ACY and divide it by a smaller number, a number less than 1. This number is going to be greater than 1. This number is going to be less than 1. So I can say ACY divided by, you know, that cosine component, 4 divided by 5, which is ACY 5/4. Cool. So I'm going to say ACY is 5 fourths. Sorry. This one is just AC. This is vector AC, or they call it force AC. So we have force AC is equal to force ACY. Use their terms, and times 5 force, which we said ACY, force ACY, was equal to PY. So we have force ACY in this member is equal to 5 force PY. Which, I mean, we really just want it as a function of P. So, we actually have to kind of go back and be like, well, we got to do that same thing. Is if P is just P, that's the magnitude of P, what are the components? Because we have a 12, 5, 13 triangle. And this is P. And then so PY is 12 13ths P. And this PX is 5 13ths P. Cool. So if we go back here, PY, what is it? It's 12 13ths P. And let's see if we can simplify this. Nope, but this we can. This will be 3 times 4, and this is 4 times 1. Did it right. So we have 15 13ths. 15 13ths P. Hell yeah. So we got our first one. And that was, you know what I mean, taking the pin as your free body diagram, but still knowing that these members can apply forces only in the direction of the members. But from the free body diagram perspective, just really looking at these pin connections as the most important thing. And let's see if we can walk our way all the way through this problem with just using the pin connections. Yeah, that'd be fascinating. Alright, hell yeah. Alright, hell yeah. And I think we should what we're gonna do is, because a lot of my method is like, hey, this is juggling, you know what I mean? And the crazy thing about like engineering and math is like you can juggle 6 things at once, like kind of your first time, and I think that's kind of amazing. But then, when the balls all fall down, it's like, I don't know, like the effort it took to juggle 6 things, well, it was a long process. It took me 3 hours just to kind of get to there. And it's just like, well, so here's the analogy. You're trying to juggle the 7th and 8th ball without going back and going all through the motions to see how you juggled 6 balls in a row. So that's kind of what we're going, like, that's, my method is just like, well, if you can do it once, man, you should be able to do it 10 times. Even, it's going to take the same amount of time each time, but, like, 10 times it sticks. You know what I mean? If I have to learn a derivative, or like a proof, like I do, if there's a proof, I need to do it about 10 times before it's just like, nope, I never have to do that proof ever again. I don't want to, because it's usually a long process. Alright, because, yeah, and so let's get a little crispier. I want to use all open arrows for these, yeah, anyway. And then so we have PY, and what did we say it was? So we can even just do it very fast. You know what I mean? Now it's 12 13ths. I don't know, you know what I mean? I think there was a time that I wouldn't be able to. I graduated college without wanting to use a triangle like this. I don't think there's any way. But we're just saying, what if P was 13 kilonewtons? You know what I mean? 13 newtons. Who cares? 13 kilonewtons. That means the component in this direction is 12 kilonewtons, and the component in this direction is 5 kilonewtons. So, cool. So if P was 13 kilonewtons, 13 divided by 13, booyah, it's 12. You know what I mean? So I think that is very helping me right now. And Px is going to be 5/13 P. Cool. And we say that we know this is the direction, so we know EY is in that direction. We know that this f of x, and we know that at these pin connections, that's the other thing. We have like 1, 2, 3, 4 forces coming in here, but this pin can only have a net force in one direction, you know, which will have a horizontal and vertical component. So that's kind of also two things to keep in mind. A pin will only have one resultant in a particular direction, but it will, you know, that resultant can be broken up into two horizontal and vertical components. So, you know, we can write some of the forces in the x direction are 0. You know what I mean? But we don't even need to. We just visually can see that these two forces have to be the same. So we have Fx is equal to, and I'm just going to write 5/13 P, because these will be the actual numbers in the end that the student will use. And I'm sure for the problem, P was stated a given value, just the way that this student's problems are done. Alright, and so we have we can sum the moments about E, so let's do that. So we're going to sum the moments about E is 0. I want to use these cards so we don't get too busy. Okay, so if we sum the moments about E, we're going to have this component. We'll do the x components first. So we have a distance of 6. So we have 6 feet times 5/13 P. This is the distance, and this is the force, so that's the moment. So moment is, force times distance. But if you do it as a cross product, you're always going to do distance. You know, it's going to be R cross F. So I don't know. It doesn't matter what. And then using your right hand rule. You know what I mean? From E, I'm going to go over 6 with my fingers. And then because this is a perpendicular distance, you're always looking for the perpendicular distance. If you did the cross product, hell yeah, you get vectory on you know what I mean, and say that, hey, this distance from E to A, you know, if you want to do that, it's the moment due to this component is R cross F, and that's going to be this R is going to be EA, vector EA cross F is going to be vector P, you know what I mean, and then so you're going to have EA is going to have two components. It's going to have a negative 6 in the I component, and then a +4 in the J component, crossed with P is going to have a negative 5/13 Pi, and then minus 12/13 Pj. So I cross I is in the same direction, that's 0. I cross J. So I do this, I, J, K, just do it twice. And so if you go in this direction, it's always going to be positive. I cross J is positive K. J cross K is positive I. K cross I is positive J. If you go the opposite, it's going to be negative. Alright, so I cross J is going to be positive K. We have a negative and a negative, so we stay positive, so we're going to have 6 times 12/13 P. And then we have, and that's I cross, that's K. Oh, yeah. See, sorry about this. I really don't want to do this because we would also have to do the cross product with this one. And that just gets too much. So perpendicular distances, sorry about that. That was a huge waste of time. But hell yeah. So you have 6 feet over, and then this force down. Or what are we doing? See, I'm even doing it wrong. We have, we're doing this x1, so we have 4 feet and then 5/13 P. So sorry for that error. So 4, and then this distance is perpendicular. So 4 feet to that, 5/13, positive. This was positive, so we have plus, and that's going to be 6 feet times 12/13 P. Hell yeah. And then this one is going to be negative. We have 4 feet, so minus 4 feet times 5/13 P. Okay, and what's the other force that we're missing? Oh yeah, this has a Py component. I'm just going to put it in this direction. We've already assumed that it's in that direction, so we have, it's Fy. And we assume that Fy is in that direction from that teeter-totter perspective. Always look at things as a teeter-totter. Pull down on this. If it's not going to rotate, it also needs to be pulled down over here. That's not completely true if this is being pulled if Fx is really being pulled hard in this direction, maybe by like, I don't know, like a rope or something, you might have an upward force. But basically the only external loads that are being applied are over here. So you're pulling it this way, and so this balances. And these two torques, if you just pulled in this direction horizontal, this would balance and you'd just be just fine because those distances are 4 feet away. But the fact that you're having a downward component that's this larger distance, hell yeah. I mean, that even just shows you that this Fy has to be larger than Py. So those are the types of things that I like to get intuition with, is the fact that make a simpler problem. If I just pulled in the horizontal direction, I'm going to say it again, the distance away from this point E, if that's where we're summing our moments, is the same for both these forces. These forces are equal, and then the moments are going to be equal. And so if all I had was this horizontal force, there would be no downward component here. And I think that's fascinating. You know what I mean? But the fact that we do have a downward component over here, and it's heavily leveraged. It's 6 feet away, where this one's only 3 feet away. And then, well, no duh now. It's just like this has to be double this. And so let's see if that's the case. You know what I mean? And so that's what we're on the road to find out. And so we have this Fy is a negative moment. So we have negative 3 feet Fy. And this all has to equal 0. And so, cool. And this got a little bit messy on me. But if I have this and I don't want to write a whole lot, I need to get this to the other side. Just make it equal. There you go. And then now it's on the other side. Booyah. What else? I'm going to, see how this is 4 5/13 P, and this is 4 5/13 P? And so those cancel. Hell yep. Positive and then negative. And then, hey, we're on the right track because we have a 6 and a 3. And didn't we say that we needed a factor of 2? You know what I mean? We're kind of shooting for that. So hell yeah. So like right here, we have 6 12/13 P is equal to 3 Fy. So Fy is just this divided by 3, which makes 2. 2 times 12/13, which is just 24/13. So we have 24/13, and then P. That's Fy. Hell yeah. So this is going to be 24/13 P. Dang it. There you go. P. Alright, hell yeah. So I love using that a little bit of, like, your algebra is going somewhere. It's also, like, good to, I like to take a step back, because I don't know. You know what I mean? I think some people are better than others. I'm just kind of starting. I like to use the teeter-totter approach. I like to see, hey, that force is leveraged. Anytime a force is, the torque is going to be, that moment's going to be bigger, I think of it as leverage. And obviously it's linear, where that's twice the distance. It's going to have twice the leverage, and it has to balance over here with half the leverage. Cool. And now we know what Fy is. And so we just know what this Ey is. It's going to be 3 times, and this is a teeter-totter approach. You have a heavy dude over here and his kid over here, and you have reversed that. You have a light kid that's half the weight of the adult. The teeter-totter will be balanced if this distance is half as, you know what I mean? So that's kind of the teeter-totter approach. But what's going to happen to this force? You have double the weight, single the weight. That means you're going to have 3 times the weight here, and that's what we're going to visually see. This is going to be 12/13. This is 12/13 times 2. And so now you're going to have 12/13 times 3. And again, this 13 is a hella prime number. And so, it is not divisible by 3. And so, 13 only factors, it's a prime number. It only factors with itself. So the second I get something to say 26, then I can start factoring. So anyway, so I guess I'm just saying that it's going to be 36 thirteenths. So this is 36 thirteenths, and I don't think I need to simplify anymore P. Alright, booyah. And hell yeah. And now we're going to go back to our pivot point at point A. And just kind of clean that up and do that again. Well, and when we know that we can kind of do it a little bit faster. We know that the vertical component has to be equal to the vertical component of force AC. But yeah, let's draw it in. So we have our free body diagram of this, of our pin at point A. And we're pulling on it. There's going to be 3 forces pulling on it. One is these 2 forces at P. And so we have PY, PX. We have an AB. And I'm just going to assume it's going to be in this direction. It should be. Well, that's not the one I should assume first. Alright, hell yeah, some more juice. And let's see where we're at, because I said that we might know AB, but nah, because we do know that we have a PY. I need to drink some more water. And then of this force AC, we have a component in the Y direction. It has to equal PY. And so, so this is going to be force AC in the Y direction has to equal PY. And if this is down, this has to be up. And if this is up at this angle, it's going to have a component that way. That component is that way, plus this component. So now we can definitively say that AB is that way. Cool. Because if we had a scenario where we have this point A, and we have a force this direction, and then we have a member AC in this direction, and then we have to have these components to balance. You know what I mean? Like this component has to balance with that component. The y components have to balance. That means that we have a net force this direction. And who knows, because this has a force that way, this has a force that way, who knows which one's bigger? So in that situation, we wouldn't know which one's bigger, and then we wouldn't know what the net force on AB is. And maybe these cancel. But in our situation, I know that I'm going to have an upward component of this AC, and I know that component's going to have a component that way. This has a component that way, and so surely AB has to have a component this way that's bigger than both of those two, or the additive of those components. So even just right off the bat, I know this component AB has to be bigger than 5/13 P, and it's going to be 5/13 P plus this component. And so let's see if we can do this kind of fairly fast, because I want to kind of work on my speed. We just said that we know that the y component of AC is 12/13 P. And we just talked about how if that is a component of a right triangle, the hypotenuse is the vector, and that's going to be the force AC. And so we take this number and we divide it. I kind of like to think of it as dividing by a smaller number. That smaller number is associated with the cosine of this angle, which is, and the cosine of, let's say, this angle right here is this value divided by the hypotenuse. So that's 12 divided by 13. So we're going to have 12 divided by 13. Dividing by a fraction is the same thing as multiplying by its reciprocal. And cool. So we have AB is just P. So we have force AB is equal to P. And yeah, that's wild. I mean, isn't that pretty wild? That if I pull a force here, this has to be P. And I might have made errors. You know what I mean? You never know. But I think we're pretty good so far, because we knew that this P would be 12/13 and 5/13. We used that to figure out that this got to be double. And then we used that to figure out, well, actually, we didn't use any of the global equilibrium to come back to this point A. So that's kind of fascinating. We just looked at the pin and said that we're going to have a component that way and a component this way, and this component has to balance. Oh, see, I did make a mistake. Holy hell. This triangle, that's going to get me all day long. This ratio of 13 as the hypotenuse, 12 and 5, I'm glad I, threw on the alarm bells. Because this is what we're looking at. And this is a 3, 4, 5 triangle. So this is going to be 3, 4, 5. It's also good to play around with this triangle and be like, well, it'd be sweet if we knew, like, just divide by 5. You know what I mean? Divide everything by 5. And now you have a, and sometimes that's kind of hard to see. Let's come over here. So this is going to be, instead of doing a 3, 4, 5 triangle, double it, do a 6, 8, 10 triangle. This will be really easy because now you can divide everything by 10. And then you can see that this is a 1.6, 0.8 triangle. And so, hell yeah. So then you have that 80%. If this is length of 1, this is 80%, this is 60%. And so, so we know that the y component of AC, we said that was py. Oh, we're getting busy. And that's a 12/13 P. If this is, and again, we need a bigger number to get this hypotenuse. So we're going to divide by the cosine component. And that's going to be dividing by 0.8. That's going to be dividing by 8 divided by 10. That's the same thing as multiplying by 10 divided by 8. So hell yeah. So now we can, this is 3 and 4, this is 2 and 4, the 4's cancel. We're going to have 30. Oh, why can't we factor out something more? Oh, yeah. And then a 10 and a 5. This is a 5 and a 2. So these 2's cancel. And we'll have 15 thirteenths. So 15 thirteenths P. Cool. And that's going to be force. And I don't even know where the hell. I'm just talking about force AC still. I found its Y component. And I know that the actual component of the force AC is bigger than the Y component by dividing by that ratio. And so we have the force AC is 15 thirteenths P. Alright, I'm satisfied with that. And I'm just going to make a card of the forces that we know. Now I'll just write them on here. So we have this force AC is equal to 15 thirteenths P. And it's going to be pushing, and so that's going to be a negative. That has to be in compression. So if AC is in tension, it's that would mean that it's pushing this pin that way. Oh man, I'm gonna struggle with that. Yeah, I said that wrong. So we started by just saying, hey, we have a chunk of metal right there as our pin. I'm pulling down on it, you know, and then so I need to push up on it. The only way to push up on it is to have our wrenches, you know what I mean, if point A is resisting that push up, the only way to push up, this wrench is in compression. So a pushing bar is in compression. So if a rigid bar pushes on something, then it's in compression. If this point A was being pulled, you know, in this direction, well, hey, I would, and I needed to keep that point A from not moving, then I would have to pull on it. Cool. All right, so that's going to be in compression. Alright, hell yeah, we haven't solved much, that's for sure. So we can go to this, we know what the force AB is. And this one should be real easy because, hey, the force BD has to be the same because we just said perpendicular forces, you know what I mean, they don't, you know, the way vectors add is this can't resist that force at all. And so, cool. So let's do pin B. And, oh, bummer, man. I mean, we haven't even finished pin A. Holy Toledo. Okay, so back to pin A. We have PY. We have PX, those are known, and now we have, I'm just going to call it AC, even though, like, they were calling it force AC, I'm just going to call it AC. That's going to be the force, because then I can easily say AC Y, because it's really difficult to do this, for me. So I have force ACY, and that's going to be in the opposite direction. Whoops. So we have ACY in that direction, and we have ACY in that direction. Sorry, ACX in that direction. ACY, ACX. Oh yeah, so if we know what force AC is, ACX is bummer. Maybe I will keep this. Force, yeah, because that's how the paper was laid out. So we have force ACX. Good enough. And if we know what AC is, ACX is just 60% of this, or it's going to be what we call 3/5 or 6/10. You know what I mean? So take this. So we have negative 15/13 times 3/5. This is 3 times 5. The 5's cancel. So this is going to be negative 9/13. So we have negative 9/13 P. And might as well, what was the force ACY? That was just equal to PY. And PY was, well, equal and opposite. Well, I mean, equal and opposite in the fact that we either need to know whether these members are in tension or in compression. And if this one's in compression, it's pushing on that point A. And so because we have a downward component due to this force, we need an upward component, which is a negative or compression force. So this is going to be negative 12/13 P. Cool. Okay, so yeah. So back to the free body diagram of pin A. We have the two forces Py, Px. We have, so let's draw those in. So we have Py, Px. We're going to have, these are in compression. It's going to be pushing forces. And so, oh yeah, this is what's tripping me out. Like, this member in compression will put a force FAC on this pin. But this pin will put a force this direction onto this member. And so let's talk about that. So again, if this pin is being pulled down or this way, or just being pulled into the direction of this member, and I need to make this pin visibly static. You know, from a statics perspective, I know there's a force acting on this pin, but the pin's not moving, so there must be an equal and opposite force in that direction. And therefore, this member is in compression. All the molecules are being compressed. What we say on this pin is there is an upward force due to this member. So force AC is in that direction, but this pin itself is pushing down on this member. So if we did a free body diagram of this member, AC, we have force AC in that direction. And because it's a two-force member, this has to be force AC as well. But on this pin, again, we have this is force AC, and it has component upwards and over. So force ACX and force ACY. And then force AB is just in the X direction, and we know that it's acting on the pin. And so let's do this again, because we're this is gonna be in compression, and we're pulling this way. And so this downward force has to be held. Yeah, we got a couple of these. All right, hell yeah. So this pin is being pulled this direction. Now this is in compression just a little bit from this downward force. I can hold that downward force back a little bit, but this has to hold the sideways force. And then so those act together, and then I can pull this in the direction of P. And what's going to happen is, even on my fingers, what I can tell you what's happening is I'm pushing up with my thumb, and I'm pulling this way with my finger. So that is a visual demonstration of, if I pull on P this way, I have to push up with my thumb, and you see that, and then over with my finger. And so this is going to be in tension, this is going to be in compression. Because this is in tension, this is pulling the pin that way. So we show that on this diagram as pulling the pin. This is FAB. But on the member AB, we would say it's this direction, FAB. And you can see that this is FAB, and these are equal and opposite. All right, sweet. So I think that was a fairly decent explanation. All right, hell yeah. So we should know what FAB is from this free body diagram. Holy Toledo. Let's just do it visually. Is that so we'd have to sum the forces in the x direction to be equal to 0. And so we have this one, we have a negative 5/13 p. That's due to p of x. We have FAC is in this direction, and we have a negative, the x component of that. And these negatives, you know what I mean, when we get that, these are internal reactions. And so these are the answers for the internal reactions. I would still double check the fact that you're saying, hey, this is in compression. That means it's pushing on a pin. Or it's in compression. That means the pin is pushing this way on the member. You know what I mean? Say those two things, because that says the equal and opposite. We're analyzing the pin. And so the pin is being pushed in that direction, and it's going to be the negative x direction. So we have negative 9/13 p. And so so we did px, this acx, and those are the only two. So if we look at pin, it has this force, and this force. This has an x component, this has an x component, and this just has an x component. And we're gonna assume that's positive. So we say positive force AB is equal to 0. Cool. That's the same thing as putting the equal sign here and making these positive. Hell yeah. Save ourselves some juice. And 5 plus 9 is 14. So we got 14/13 p, and that's equal to FAB. So force AB is 14/13 p. And again, I might be getting, there might be errors all the way through this, but the general gist, hopefully, we're getting. And hell yeah, and now we just know the force in the x direction at pin B. Hopefully we can visualize that. Take the chunk of metal that is pin B, and this is in tension. And so if I say that, pin B is just chilling out here, this member is in tension, then pin B is being pulled by that member. So FAB is being pulled by that member. Same thing at the reaction of A. We said, hey, this pin A is being pulled that way. is being by this, it's being pulled that way by this, and so it has to be pulled that way. And so the pin being pulled that way by FAB is a sign of tension in FAB. Again, pin A being, pin A being pulled this way is making AB in tension. Same thing at B, pin B. If AB is in tension, it's pulling the pin this way. If the pin is being pulled in this X direction, it has to be balanced by another force in the X direction, and that's member BD, and that's also in tension. And so FBD is 14/13 P. Alright, now when we get to here, this isn't the same because this has a component in the X direction. So if we look at pin B, alright, hell yeah. So if we look at pin D, sure, it's because of this tension, it's being pulled in this direction by force BD. It could be resisted by this force, but this can also resist it. This could either be in, this has a component. We don't know whether it's in tension or compression, but it could have a component that way. It has a horizontal, this force, aligned this way or that way, has a horizontal and a vertical component. Oh, so now we can go to pin F, you know what I mean? And so, hell yeah. So pin F is a chunk of metal, and we know its reactions. You know what I mean? These are the forces. And then let's talk about this. This is the forces for the whole structure. The whole structure is like this structure is being pulled this way and pushed up, and it needs to be pulled this way and pulled down. In order to do that, this pin goes through the structure. So I always have to talk my way through this. This pin goes through the structure and is pulling down and pulling over. So these reactions at the wall are what the pin is doing on the structure. Cool. So the pin is pulling in those directions. So that reaction is what the pin is seeing. Yeah, fair enough. Yeah, I'll buy that. You know, could be wrong, but yeah, I don't know. I think it's tricky, the kind of the equal and opposite. I don't know why I get kind of hung up. But yeah, the structure as a whole needs to be pulled this way and then pulled down. And I drilled a hole into the structure. That's why even taking this, even though it's just bars, to actually kind of make it a totally rigid, or just a like a cutout of steel with a hole in the end, and be like, okay, I'm going to apply that force in that direction, whatever this resultant is. Alright, hell yeah. And if I'm going to talk about the equal and opposite, say it both ways. Because this rigid structure is wanting to take the... Because this pin is still in a flange. If we look at like a downward section, like here's the flange, and then here's the pin that goes through. And we can just have a loose pin. And then here is the two bars. You know what I mean? So here's maybe one bar coming in, and then adjacent to the other bar. And then so those also have holes, so just kind of a top view. And so, and obviously just looking totally straight down, these bars kind of diverge in angle. But yeah, this whole structure wants to move this way. And so the bars are pulling away from the wall. So these two bars are pulling away from the wall, and they're pulling on that pin. They're pulling this way on the pin in the X direction, and they're also, as this rotates around, it's actually pushing up. You know what I mean? So it's pushing up. So that's what this structure is pushing up and pulling away from the wall. And that's going to be equal to Fy, Fx, Fy. So yeah, so that's just kind of two ways to look at the reactions. This structure is pulling on the pin with those two. Pulling on pin. The pin, from Newton's laws, is not traveling across the universe in that direction or that direction. So something must be pulling. So if this structure is pulling on the pin that way and this way, something must be pulling on the pin equal this way and equal that way. And so I think even just drawing this is something that I dislike, but it's something I need to get better at. You know what I mean? Like looking at, you know, I mean, it looks like this. You got the same redundancy going on, but yeah. And so again, the structure is pivoting around this point. It's being pulled this way. This point's going up and over, and so it's pulling the pin in. It's pulling the pin up and over. I mean, just thinking like, yeah, sure, the pin is like just thinking of the pin as fixed. Somehow the pin is fixed. I mean, because when you do these statics problems, it's like everything's not moving anyway. So it seems like everything's kind of fixed in place, but then you have a pin that's kind of freely floating about itself, so that's kind of fascinating. But you know, it's fixed in the regards that we don't see any motion. You know, this pin isn't traveling horizontally, vertically, or rotating about the universe. And so, but we got stuff that's pulling up and over on this pin. Pin's not moving. Pin must be being pulled down in this way in the same direction. I mean, with the same magnitudes. Cool. And so, how do we want to draw the free body diagram on the pin? Holy Toledo. Oh yeah, that's tripping me out, the fact that I just kind of did the same. But yeah, but what happens is that, sure, this structure can push up and pull over. But it does so by the reactions of these members. Like this can be in tension or compression, and this can be in tension or compression. So these two forces in the F and X, or the Fx and Fy components, are what's going on with those. And so, and we already found the reaction at the wall. So yeah, so you have a Fy is 24/13 p. You have an Fx, which is 5/13 p. And that has to be balanced with a force this direction and a force that direction. Now, again, this might be one where this is in, this one's in compression. Let's try to visualize it. Let's just take this 3-bar system, and we know I think we're basically kind of pulling this way. Cool. So if we pull this way, then this one is going to, you're just going to have a force in the horizontal over here. If I pull if I just push straight down, this one is going to compress, nothing's going to happen. I think it's very useful to do like the simplest thing first and then add complexity. And then so if I pull at an angle, let's say I pull down at this angle, then this 3-bar system is having a tendency to rotate this way about this point. And so the force generated would be this way to balance that. So I would have to pull down on this structure over here. Alright, hell yeah. I just went through that just because I was overthinking it. And again, we're in that same boat. We have a Y component that's being pulled down. That we need a downward force to pull. See, yeah, I get confused of like what's like looking at the pin or the structure itself, or is that the same thing? The pin is going through the structure, and we said that the reaction of the pin is doing what's needed on the structure to keep it just from... Because if we remove this pin, the structure is going to just rotate this way. It's going to go up and then rotate, and so we need to have this reaction, you know, from the pin onto the structure. We need to pull, and then that pin is... does that mean that pin is being pulled in those directions? Yes, because I am pulling this pin. It's the same thing over here. I don't know why this is so easy to see that you're just like, hey, I'm just loading this pin in that direction. Well, I'm just loading this pin with these forces. And I know that the pin's not traveling this way and this way. And I know it's being balanced. And this force in the Y has to be balanced with, we're going to call this force EF. Force EFY. And so hell yeah, so this has to be balanced, and this is going to be a downward force, and again this has to be in compression. Then if this is a downward force, this has to be in compression. Cool. So FEY. Oh, man. So force EF in the Y direction has to equal this force. And we're going to put a... I don't know if I want to put a negative or positive on this, though. I mean, on here it would be a positive force. I mean, if this is down, I would need a positive. So yeah, let's do this. So we have EF in the Y direction is going to be a positive 24/13 P. Alright, hell yeah. I'm glad I'm going over this because this is what trips me out the most. I've just been talking about how we have this pin, and if it's being pushed upon by this member, so let's do that. I mean, I can always just take out this wrench, throw the pin in, and if I'm using this member to push upon this pin in that direction, this member is in compression. Now, this force is upward, you know what I mean? So the Y component is going to be positive. And so, yeah, so on this, due to this member, sure, this Y component is positive. So we have 24/13 P. But just in general, FEF So if I just wanted to know what FEF is, that is going to be a negative. This thing's in compression. This negative sign indicates compression. And it's going to be bigger than this because this is the component of that. And if this is the y direction, this triangle is a 3, 4, 5 triangle. And we know the cosine component. So we're going to take this value and we need to make it bigger by dividing by 4/5. That's the same thing as multiplying by 5/4. So we're going to take this number, 24/13, and multiply by 5/4. 24 goes to 12 and 2, which goes to 6 and 4. The 4's cancel. We have 30/13. Alright, so we found what FEF is. It's 30/13 P. Cool. And EY had a component of 30/13 P. So let's just do this real easy. And because well, no, we gotta slow down. Hey, because this is the y component. I was gonna do something stupid. But okay, so we have the y component of this. Well, we should kind of slow. I was just thinking we could get this one fairly fast, but let's just stick on one at a time. Because we haven't finished F. We found one component, that's FE of F. And yeah, I don't know why I have to do this every time. If this one's in compression, it's pushing that way. So yes, so FE of F pushes that way. And here's the reactions of the pin from the wall. We know what those are. We know what FE of F is. And now we just want to know what, and it looks like force DF is going to be that way. So this is force DF. And now we should do the sum of the moments in the x direction, because this is in the x direction. And we can get this force EF in the x direction. That's 30/13. And this is a 3, 4, 5 triangle. It's 3/5. So we got 3/5. This is 6 times 5. The 5's cancel. This is going to be 18/13 P. So that's going to be 18/13 P. And so now the sum of the forces about F, we have 13/13. Sorry, 5/13 P. There's one of them, and that's positive, in the positive x direction. We have this one, which compression was pushing. That's also going to be in the positive. So we have plus 18/13 P. And at this point, I don't have anything to like double check my answers. You know what I mean? I think seeing if I don't know. Yeah, I mean, if you solve everything, everything should balance. You know what I mean? So unless you have something kind of funky going on that cancels itself out. All right, so 18 and 5. 18 goes to 20, 23. So we got 23/13. So yeah, 5. So we have this reaction, Fx, and we have this in the x component. Those are the only two. We have the reaction in the x, this component's x component, and it just has to be balanced by that. And so that has to be in that direction, which is going to be a negative. So we have F D of F is going to be a negative 23/13 P. Oh, but I don't want to, yeah, that's just the x component. See how we do that? The x component of this, and that's not really true. Well, yeah. Yeah, that's why the equal and opposite gets me all the time. Because our pin, here's pin F, and due to this member, DF, we have a force in this direction. That's FDF of X. And that's in the negative X direction. So, I mean, I should say it's, assume it's positive, but then it's in the negative 23/13 P direction. Because that's the pin, and that's the force due to DF, and it's pulling on it. If it's pulling on it that way, that means that this member is in tension. This member is in tension if it's able to pull that pin that way. So let's skip this half step and say force DF is a positive 23/13 P. Because at the end of the day, we really just want to know the actual members and what they're, whether they're in tension or compression, positive or negative, and what their value is. All right, hell yeah. So we're doing pretty good. We found that member. So if I found it, I'm just going to do a couple lines through it. We found EF, got that. We found BD, and AB. And did we find AC? Hell yeah, we found AC. So the only members that we don't know are these ones. And cool. So now I can go to this one. At D, I know that, hey, this component is an X component, this component's an X component, and they're different. This is a vertical component, and this will have an X component and a vertical. And so I know this X and this X, I don't know this X. This doesn't have an X component, and so booyah, that'll be the next one we do. So we're going to take this pin D. Now let's think about this. This member is a positive. So this is in tension. And here's pin D. So if this member is in tension, it's being pulled that way. So we have FBD is 14/13 P. This one we also said was in tension. So even though it's pulling on F in tension, hey, guess what? It's also pulling over on D in tension. Because if F is a fixed point, or like a pin, and I'm pulling on it, yeah, I don't know why that trips me up. We just said that this member is pulling on pin F, and therefore it has to be in tension. And then we go to pin D. If this member is in tension, it must be pulling on pin D. Yeah, it's just kind of, I don't know why that, I have a hard time with that. But anyway, and that's going to be force DF. 23/13 P. Cool. And then let's just do this one, because we just know that we have a component, force CD of the X direction. And cool, this one's bigger. We can even do mental math. It's almost bigger by 10. It's bigger by 9. So we got 9/13. So this is equal to 9/13 P. If this was 9/13 P, we'd have 9 and 14. That would be 23/13 P. And that's what we have to balance. Cool. So if this is that X component, Same thing. This is a 3, 4, 5 triangle. We know it's this component. I'm going to divide this by 3/5, which is the same thing as multiplying by 5/3. And this 9 is 3 times 3, so a 3 cancels. And I'm going to have 15/13 P. So this member has to have a component that's pulling. So I need this is pin D, and I need this member to pull this direction on pin D. The only way it can do that is by being in tension. So we have FCD is going to be 15/13 P, and this is a positive. Hell yeah. Oh hell yeah. So right here, this is like the, what do you call this? Like a red herring? You know what I mean? Just something that looks complex. I don't know. I think I'm mixing up my adjectives. But so cool. So right here you have tension on pin B in both directions. I don't know why I just didn't see that. This has to have 0 tension, because if I have this scenario where I have pin B and it's getting pulled this way, it has to be equally getting pulled that way. Now, if I could span my hand from there to there, what would happen if I just pulled up on pin B? You know what I mean? These tensions can't do anything for an upward component. So if that were the case, if I had any upward component here, it would just move upward. There'd be no way to prevent that. And it doesn't look like it. It looks like a rigid structure where you'd just be like, well, it feels like you can't even, it wouldn't be able to move that way. So let me pause the video. Alright, hell yeah. I think I tripped myself out by saying, like, if I have this as pin B, I could have a load on pin B. There's no reason why I couldn't just pull up on pin B here. That would cause this member right here, this vertical member, to be in tension. If I pull up on pin B, this is the only thing that's holding this tension. Just pretend this is just rigid to a wall or something, doesn't really matter. But then, yeah, so there you go. So if this one was up in tension, I would have to have something down. So like these would have to be in compression. And I don't know, it'd just be kind of fascinating to like get rid of this force and just put an upward force at B. And, you know what I mean, would everything jive? Well, this would hit the, if this is my pivot point, and just pretend like this is an actual, like let's say this was the pivot point and this was the roller. And I pull up on B, like could I do that with this structure? It would teeter-totter around this point. So an upward force would have a moment, and then that moment would have to be resisted by this force if this was the pivot, and we do have that. Alright, I have to throw in the towel on kind of analyzing if I had a force at pin B. That'd be another problem, and I can barely wrap my mind around this one. And so, but yeah, it's kind of cool. There is no force, so force BC is 0. So that's cool, you know what I mean? I mean, I guess I graduated in this class, but man, you might just spend like a week on this and then you move on. And you do a couple problems and you're just like, I hope I never have to do that ever again. And yeah, it's interesting. I did environmental engineering where I didn't move on to the structures classes, and I guess other students, yeah, they would do like structures 1, structures 2, and I did not take those classes. It's kind of fascinating. So I just have this, you know, sophomore year level skills. But I mean, if you kind of master these skills, you know, it's just all the same. It's just more complex. I moved on to like water and hydraulics, but not that I remembered any of that. Holy Toledo! This was my most fascinating, material mechanics and yeah, just kind of mechanical engineering type stuff. And hell yeah, civil engineering is just bigger design mechanical engineering. Cool. Yeah, we're almost there. We got that one. And so this is the only one that we don't have, because at this point C seemed like difficult. You're just like, well, I got a lot. got 4 forces going on, and finally we're going to be done. And that's literally everything. And so point C, because we need to know this CE, and just in general, we typically don't need to draw too much, but we're just going to assume the positive direction. So we're going to say sum of the forces in the x direction. I guess I can do that. Sum of the forces in the x direction have to be 0. So we're going to say force CEX is going to be positive that direction. This is going to be, yeah, I have to do this every time. This one's going to be in tension. And so if this is in tension, cool, it's pulling on that thing. So compression pushes a pin, tension pulls a pin. I don't know. So that's going to have a positive component. So we have 15/13 P, and we just have this component of that. Alright, booyah. Alright, this is point C, pin C. And the cosine component, I don't know what I'm saying. Just this component, the horizontal component due to this triangle is 3/5 of that. Cool. So we have 3/5, which this is 3 and 5. 5's cancel. That's going to be 9/13 P. Alright, hell yeah. This one is going to be force AC, and we just need the x component. This force AC is in compression. Compression is pushing on that pin, and it's pushing in the positive direction. Oh, so cool. So we just said that this is pulling in the positive direction. This is pushing in the positive direction. So now we know that CE has to be like kind of getting fairly big. You know what I mean? So FCE is in the positive. This is in the positive. This is in the positive. This is also in the positive. So we have plus, and then here's the x component, 9/13 P. 9/13 plus 9/13 says 18/13. And these are getting to the other side. That means this is going to be negative 18/13 P, which acting at C is just going to be in that negative direction. So we have 18/13 P. That's going to be CEX, force CEX. So if I say this is point C, pin C, and I need to push this direction, that makes this member in compression. So now I know that force CE is negative 18/13 P. And we are done. Okay, sweet. And so, and it's interesting that this is FCEX and then FCEY. Now, depending on, because I was talking about this member acting on this pin. So let's talk about that. This is in compression. This member CE is in compression. And so it's going to be pushing on this pin over here this way. So this can push at C, it's pushing in the negative x direction. But over here at pin E, in compression, it's pushing in the positive x direction. So we solved for, we would say like, hey, at pin C, the force CE in the x direction, is that direction, which would be negative. But it's going to be positive this compressive force of this member is going to be positive if it's over on pin E. So it's just that's kind of the equal and opposite. So this is going to be the sign convention for whether the member is in tension or compression. But if I say what the components are, what sign convention am I going to use? Do I just stick with the negative convention and say that, because that was the only thing that was tripping me up, is if I analyzed a pin, I would say the member was causing the force in a particular direction of that pin. But then that force was associated whether that member was in tension or compression. So these positives and negatives on not the X and Y components of the force, but just on the force in the member, are just due if that member is in compression or tension. Has nothing to do with the horizontal or vertical positive or negative directions. So I guess what I would do is say this, like, because I solved, so if I wanted to get really technical and do this again, I would say at pin A, because that's kind of what we were analyzing, like the first one we were analyzing, or we can just even do this. At pin C, this is going to be negative 1813P, and then just write pin C. So now I can see that the force due to member CE in the X direction at pin C is going to be that direction. You know, and you know, hey, if this force is in tension, then it's just being pulled. So hey, it's being the component of this member on pin D is going to be that way and that way. The member on this one is going to be this way and that way. So yeah, if this member CD is in tension, then it's going to pull this pin this direction and that direction. If this is in tension, it's going to pull it that direction and that direction. Okay, yeah, so that's kind of tricky to get used to. And so if I said the y direction of this at pin C is just 0. Alright, so now I kind of want to go just to kind of double check my work. Alright, hell yeah, I thought of a way to double check my work. So we have member, so let's just do this. So member AC is force AC. And that's going to be in compression, and it's going to be negative 15/13 P. And then so we're going to get the X and Y components, and so I can just do this. Cool, and that's going to be 4/3. So we have this. We have 4 and 3, and then 5. So this component is going to be 4/5, 15/13. This leaves a 3, and we got 12/13. So this is going to be 12/13. Hell yeah. And then this component is going to be 3/5 of this. So we have 3/5, 5, 15/13. So this is 3 and 1. We got 9. Cool. And I'm sure this is going to pop up quite a bit. Let's see. So because this is P, we have 12/13 in this direction, P, and then we have 5/13 P. So sweet. And then this would be P. Hell yeah. And one P on that one. Cool. AB, because it's horizontal, we just have, so just write force AB is positive 14/13 P. You know what I mean? So now we can start kind of checking, because at A, we're going to be 5 that way, 14 this way, so it's going to be a resultant of 9 this way, and this one has a resultant of 9. And if this is in compression, it's pushing. This is in tension, it's pulling. So now we can see that intuitively. You know what I mean? That's where I'm trying to get faster at getting intuitive. Pulling 14, pulling 5. That's a resultant of pulling 9. This one's pushing 9. Force BC is 0. Force BD is the same. It's in tension, 14/13 P. Force DF is 23/13 P. And let's see. Our reaction is going to be, how should I do these reactions? Yeah, so these reactions will be with sign convention horizontal. So this is f of x is 5/13 P, and then this is downward force in the y direction, 24/13 P. So these are the directions of those forces, and this is the positive values expressing those. Alright, so EY, and I guess for these I'm just saying the F for the force, I'm just saying the letter, and that's fine. So EY is the force at this, and that's going to be 36/13 P. Let's do this one, because we're going to have, how should I do this? Yeah, let's do this. And we have force EF is 30/13 P. This is a 3/4/5. So if we wanted to get this component is going to be 4/5 30/13. This is 5 times 6, 24. So we got 24/13 P. This is going to be 3/5 30/13. This is 6 and 5, so it's going to be 18/13 P. Yeah, that's what we had. I'm just going to kind of doubling up. And let's try it out. You know what I mean? If this pin is being pulled 5 this way, this is a positive. So tension on this is being pulled 23. So 23 this way, 5 that way. It's a resultant of 18 that way. So this has to be 18 that way. And yes, this is in compression. Well, did I get the sign right? This has to be in compression, right? I don't think I got the sign right on this one. Yes, because if this is being in tension due to that force, I have 5 being pulled that way. So I have a resultant tension And so I need this to be in compression. Yeah, it's a bummer I didn't get that. I don't know why I don't have a sign convention on that one. I mean, I did it from this diagram. Yeah, do we need to walk through this again? This one's in tension, compression. I'm sure I did some of the forces in the X. And some of the forces in the X say that this is 23. And so we need something that way. This force... Oh, no. This is that way. To balance it, I need a force that way. That's probably where I got confused. So at this pin, I'm pulling 5 this way in the X. I'm pulling 23 this way in the X. I need something that pulls 18 that way. And to do that, I need this member to push, be in compression in the X direction of 18. So yes, this member is in compression, and we got our negative sign. So we have negative. And I guess on these I should just put negatives just to emphasize that it's in compression. Cool. Alright, and so let's see. So force CE is negative 18/13 P. And then this is kind of one of the last ones. Force CD is 15/13 P. And we're going to have a 4/5 component. So 15/13 times 4/5, that leaves 12/13. So we have 12/13 P. FCD is positive, so let's just get some positives on these. We have 3/5. 15/13 times 3/5, that leaves 9/13. Cool, and let's just double check this. You know, some of the forces in the X direction, if this is in compression, we're going to have a 18 that way. If this is in tension, we're going to have a 9 this way. So that's still a resultant of 9 that way. This is 0, and this is in compression, so that's pushing that way 9. So that balances it. This one pushes that way 9, this one pulls that way 9, and this one pushes that way 18. Hell yeah. Alright, so we did it. And I don't think I have a voice to make a shorter video tonight, so I'm just apologizing for this student to make a 4-hour video on him. You know what I mean? It's just all for fun. And so, but yep, I said my videos are long. You're just going to have to search through what you need. But yeah, this is, I mean, I'm getting deja vu of just the whole method of doing problems. You know what I mean? There's an aspect of not wanting to make mistakes right at the get-go. You know what I mean? So just really a slow process. And I like to, I don't know, just kind of, yeah, do these examples to just figure out what the theory is going on. You know, just to develop intuition. And you even saw it of trying to pull on point B. It's just like, I don't know, that seemed too complex. And it gets complex because it's the sum of the moments. You know what I mean? Doing these things of like taking something like this and turning it into a teeter-totter, putting a heavy person over here, hell yeah. Well, the heavy person over here and a light person pulling down at twice the distance. Same thing as a heavy person pulling over here. So that's where we get this 12/13 and 24/13. So those are kind of the intuition things that you can kind of pull out. But I'm glad I came up with a system to show what the internal reactions were, either negative or positive, compression or tension, and then finally figuring out that, hey, like obviously this in compression is going to be pushing that way on point C, in, you know, I mean, kind of in maybe the negative y and positive x direction, but this in compression is also pushing on point A in the negative x, positive y direction. So it's kind of that equal and opposite-ish. And again, I don't know if this is 100% done right. I mean, obviously there might be errors. Sometimes I realize that the errors come from like a big, I don't know, like the worst errors are when you're getting the theory wrong and you're doing something algebraically correct, but when the actual theory says you got to go down a different path, like a divide by 2, or you know what I mean, that stuff is mind-melting. It's really difficult to catch those errors. But when it comes to some of the forces, I think we're looking pretty good here. It would also, yeah, be kind of interesting to also, because all we did was, take the reactions at the pin. I mean, if I wanted to go through and also just say, if I wanted to even just take this as the structure, and then I'm going to have this as a force that's pulling in that direction, and this is 0, and this is pulling in that direction. Well, if I had that, and then the reactions, like all the sum of the forces of that would have to be 0. And so let's do that one. You know what I mean? Because I have the reactions, so I have a 36 up, I have a 24 down. And so that's going to be a resultant 12 up. This is just over, so hey, you know what I mean? Without looking, this has to be 12 up. No, I said that wrong. This is, so if I'm looking at this structure right here and doing a free body diagram of it, I know that this force is pushing up 36. This is pulling down with 24. So I just want to figure out the forces in the y first, right? And so 36 up, 24 down, that's a resultant of 12 divided by 13 up. So this has to be down. So this one has to be in compression, and it has to have a 12, 13, and it does. Okay, so let's say if I just kind of visually took this and I wanted to make sure, well, now let's do the sum of the forces in the x. This is 0, and then this has a 5 thirteenths that way. This is 14 thirteenths. So this is in tension, so that's going to be a resulting of 9. So something needs to push on this structure that way, and it does. It pushes with the 9 thirteenths. Now let's do some of the moments about, you know what I mean? I think we should take the sum of the moments about here, just because, some of the moments about C have to be 0. What we're going to show is that this 14 thirteenths P at a distance of 4 feet has to equal, well, alright, hell yeah, I ran out of juice. But then, this just came to mind. Everything is divide by 13. I mean, you can just factor that the hell out. So, we're going to, alright, just running out of juice. But, hell yeah, we're going to sum the moments about point C. Again, we're taking this structure. It's going to have a force there. It's going to have resultants there, but this resultant's going to be 0. And let's see what we got. I don't know if we'll be able to do this mentally, but this is going to be a positive 36 times 3. That's kind of the value of that. 36, distance of 3, positive. This one is going to be a 14 times 4, so I think we just need to pull out the calculator, but we got 36 times 3 plus 14 times 4, and then this is going to be a minus 24 times 6, the distance 6, and then we have minus 5 times 4. And that's 0. So the sum of the forces about that point are 0. So that was a pretty good double check. And it just shows you that you can do, free body diagrams anywhere. I could take this chunk and say that I have, something pulling on it, in tension, and something pushing on it. And you do the same thing. Cool, so hell yeah. So I think I'm done with this. I don't know, tonight, do you think I can do another one, a shorter one? I think I'm going to lose my voice. I'll probably do it tomorrow. But hell yeah, I think this was a pretty decent video because it shows you the process of, like, Especially the process of like, man, um, I don't know. I think it only gets easier if you do like this just on repeat and keep adding to your skills, you know, the geometry, trying it different ways, um, and then finding ways like little shortcuts to make it mentally faster, so you're not having to just kind of hold a bunch of concepts in your head at the same time. But anyway, I gotta be done, so thanks for joining me on this one. Hell yeah, that's a video.